Tatiana Alexandrovna.
Computer. As a moderator, I will take a first word. Good morning, everyone, and a very welcome to all our attendees, both here in Khmelnytskyi and joining us online from over the world. My name is Pavlo Radyuk, and it is my distinct honor to moderate this workshop. Today, we gather to explore the critical intersection of cutting-edge artificial intelligence and the global objectives that shape our future. Our goal here is to foster discussions that will help align technological progress with the United Nations Sustainable Development Goals. This workshop would not be possible without the leadership and vision of our organizing team. To officially open our workshop, I would like to invite our esteemed General Chair, Professor Tatiana Gaurushenko, from Khmelnytskyi National University, to share a few words. Professor, the floor is yours.
Thank you, dear Pavlo. Dear colleagues, thank you all for participating in our workshop, for your interesting papers. I am glad to welcome all of you to our workshop, but unfortunately online, not within the walls of our university. First international workshop on advanced AI in explainability and ethics for the Sustainable Development Goals, ExplAI-2025, is organized by Computer Sciences Department of Khmelnytskyi National University. Our workshop ExplAI-2025 focuses on theoretical and practical advances in trustworthy, ethical AI systems for decision-making aligned with the Sustainable Development Goals. This workshop provides the platform focused on advancing theoretical and practical advances in AI, ethical AI, with the principle of the SDG. The workshop centers on the intersection of three critical areas: explainability, ethics, and sustainable development goals. ExplAI-2025 offers a specialized platform for researchers, for practitioners, to exchange knowledge on developing responsible AI solutions and contribute to a sustainable global future. I invite everyone to attend all the events of our workshop, and I wish everyone fruitful work and interesting presentations. Welcome, dear colleagues.
Thank you very much, Professor Gaurushenko, for these inspiring words. Now, I would like to invite our distinguished program committee chairs to offer their perspectives. First, let's welcome Professor Alexander Barmak from Khmelnytskyi National University as well.
Thank you. So I will say a few words. Good afternoon, everyone. Sorry for my poor English. Following the warm welcome from our General Chi, I am delighted to add my own words of welcome to all of you to the ExplAI 2025 workshop. As program committee chairs, we are incredibly excited about the program we have put together. The field of explainable AI is more important than ever as we seek to build trust and understanding in the complex AI system that are shaping our world. This workshop is a fantastic opportunity to share our latest research, exchange ideas, and foster new collaboration. We have thrilled to receive so many high-quality submissions, and we want to extend a sincere thank you to all the authors for their excellent work. Our gratitude also goes to the dedicated program committee members and reviewers for the thorough and insightful evaluations. We have a stimulating program ahead of us with inspiring keynotes and presentation. We hope you find the sessions engaging and that the discussion will spark new insights. Thank you for being here. Let's have a wonderful and productive workshop. Thank you.
Thank you very much, Professor Barmak. And I should note that your English is good enough. And now I'm pleased to welcome our co-chair, Professor Yuri Krak from Taras Shevchenko National University of Kyiv, plus Glushko Institute.
Dear Professor Hovoroshenko, dear colleague, researcher, scientist, and friend, I invite you to participate in this extremely important workshop on the development of research on explainable, transparent, and reliable artificial intelligence system that contribute to the achievement of sustainable development goals. I wish you a good presentation of your achievement in this field, fruitful discussion, finding a partner for joint research, and creation a new startup based on the result of the discussion. I also wish all participants good health and prosperity. Let's get started. Thank you.
I appreciate your kind words, Professor Krak. Your collective vision has been quite instrumental. Now, to provide everyone with a brief overview of our workshop journey and what to expect today, I'll walk through a short presentation. For that, just give me a few moments. Okay, so you can now see the presentation. Okay, let's proceed further.
Yes.
Once again, welcome to ExplAI 2025, hosted here at Khmelnytskyi National University on this 7th of November 2025. As Professor Hovoroshenko mentioned, it's a pity that we cannot gather offline, so we are supposed to meet online due to the ongoing invasion and missile attacks, etc. We are proud to affirm that both participation and the publication of proceedings are entirely free of charge for all authors. Our core objective today is to explore cutting-edge research in explainable, transparent, and trustworthy AI systems, specifically those that advance the UN Sustainable Development Goals. We were thrilled to receive 44 submissions through the Microsoft CMT service. After a rigorous peer review process, we accepted 15 high-quality papers, resulting in an acceptance rate of approximately 34%. Each paper underwent a double-blind peer review by at least 2 independent experts. Our acceptance criteria were stringent, required at least one strong accept and no rejects to ensure the highest quality of research is presented today. This rigorous process was managed by our dedicated committee. I'd like to again thank our General Chair, Professor Tatiana Hovoroshenko, and our program chairs, Professors Alexander Barmak and Yuri Krak. They were supported by a diverse international program committee of 21 members from 10 countries, including Ukraine, the US, Poland, Kazakhstan, UK, and beyond. The response from the global research community was fascinating. The 15 accepted papers feature contributions from approximately 90 authors representing institutions in at least 8 different countries. This includes researchers from Khmelnytskyi National University, Taltech University in Estonia, the Polo-Japanese Academy of Information Technology, the Astana IT University Kazakhstan, and among many others, reflecting a truly international collaboration. Here's our agenda for the day. We have 4 sessions: Explainable AI, AI ethics and governance, Sustainable Development Goals, and Trustworthy AI, with coffee breaks scheduled between them. For our online participants, please note that Zoom meeting ID and passcode on the screen. The entire workshop is being conducted in Kiev time zone, EET, so it's East European time. Our sessions are packed with exciting research. Session 1 will cover topics from sea ice forecasting to network attack detection. Session 2 focuses on AI ethics with talks on social engineering, resistant architecture, and ensemble models. Session 3 directly addresses the Sustainable Development Goals, featuring work on medical diagnostics and urban traffic analysis. And Session 4 will explore trustworthy AI through topics like fake news detection and vision transformers for public safety. A quick reminder that our presenters, each talk is allocated approximately 10 minutes, with 5 minutes for questions and answers. As per our submission guidelines, all papers, must include a generative AI disclosure and adhere to the CUR template. A signed author agreement is also required for publication. For our audience, please use the raise hand feature on Zoom or catch my eye in the room during Q&A. So I should remind you one more time, those authors who have not sent us signed agreement, please do it in a short period of time. We will be presenting awards for probably best paper, best presentation during our closing remarks and at approximately 2 p.m. Furthermore, authors of selected papers will be invited to submit an extended version of their work with at least 70 or 80% of new content to a special issue in the Sustainability Journal from MDPI. This is a wonderful opportunity made possible by our commitment to free, open access publication via CUR. Finally, I want to extend a heartfelt thank you to Khmelnytskyi National University and our armed forces of Ukraine for hosting us and for this opportunity to make a scientific contribution in Ukraine. The work presented today is a testament to our community's dedication to aligning AI with a sustainable and ethical future. Let's make the most of this opportunity to connect, learn, and collaborate. Thank you. So before we go through session number 1, are there any questions? If none, and with that, let us begin our first session titled Explainable AI. A reminder to our speakers, you have 10 minutes for your talk, followed by 5 minutes for questions and answers. So kicking off our session is the presentation Explainable Artificial Intelligence Foundations for Web-Based Sea Ice Extent Forecasting System by Tatiana Hovrushchenko and her colleagues. Please, Vitaly, begin when you are ready.
Hey, good afternoon. Can you see my screen?
Yeah, it is visible. Everything is fine.
My name is Vitaly Alexeiko, and I'm a PhD student in Khmelnytskyi National University, and I'm pleased to present a paper titled Explainable Artificial Intelligence Foundation for Web-Based Sea Ice Extent Forecasting System. Authors of this study are Tatiana Hovrushchenko, Olga Pavlova, Vitaly Alexeiko, Oleg Voichur, Valeria Shvaiko, and Artem Boyarchuk. We represent Khmelnytskyi National University and Tallinn University of Technology. Nowadays, there is a sharp growth in artificial intelligence tools that solve applied problems in various areas of human life. However, quite often AI models can be imperfect and make incorrect or suboptimal decisions that directly affect the quality of life or cause financial or reputational damage. The concept of explainable artificial intelligence is focused on understanding the behavior of an artificial intelligence model similar to how people do it. When developing ExplAI systems, it is necessary to ensure four basic principles: explanation, meaningful explanation accuracy, knowledge limits. Our previous works have considered long-term forecasting of the land surface temperature using recurrent neural network with long short-term memory architecture and the development of a corresponding information system, as well as the analysis of sea ice extent data using statistical methods and unsupervised learning methods to prepare data for forecasting. A significant problem in the development of XAI is the black box on which deep learning models are based. That is, the nature of the algorithm is not transparent, which causes users to distrust certain decisions made by the system. In order to create a counterbalance to the concept of the black box, scientists have defined the key terms: transparency, interpretability, and explainability. AI-based forecasting relies on robust datasets that capture the dynamics of time series data over time. AI models which can be used for sea ice extent forecasting range from traditional machine learning algorithms to advanced deep learning techniques. It is necessary to evaluate performance across different time horizons and examine model robustness during extreme conditions, such as record low ice years. Also, it is important to promote trust, transparency, and the effective integration of AI technologies into global climate initiatives. So in this slide, you can see our theoretical framework with key aspects, relevant theories, and application framework, and of course, ethical and regulatory framework on the basis of European Union law. And now on the slide, you can see a figure which I'm sorry, which presents, yes, our research methodology. So to avoid any risks, it is necessary to ensure responsible research. In particular, use only reliable datasets provided by international organizations such as National Aeronautic and Space Administration, NASA, World Meteorological Organization, National Snow and Ice Data Center, and other. For the accuracy of the forecast, it is advisable to use different approaches, including statistical and data mining, as well as evaluating the performance of machine learning models using known metrics. This will avoid problems of overfitting or underfitting and will help mitigate potential risks in forecasting anomalous values. To avoid legal and ethical risks, it is planned to use open source methodologies and implement a data management policy to comply with ethical and legal standards. In long-term forecasting, many sequence-to-sequence models such as LSTM and BLSTM tend to smooth out fluctuations. As a result, the forecast tends to shrink towards the mean or create flat, so non-dynamic trajectories. This is due to a number of factors, including error buildup, which makes the model cautious, training loss, which increases with deviation, so the network starts to predict average values, and the lack of explicit seasonality, which leads to a loss of model amplitude over time. There are two approaches to building ensemble models. First of all, conventional or training and residual-based sequential training. Conventional or parallel training trains both SARIMA and recurrent neural networks on the same input time series. Thus, both methods produce forecasts independently, and the final forecast is a combination of the weighted average forecast of both models. The advantages of this approach are simplicity of implementation, the ability to take into account different aspects such as linear and nonlinear trends by each of the models. This helps to avoid the dominance of one model over the structure. However, this approach has a number of disadvantages, including redundancy in the case when both models try to learn information that is overlapped by the other model. And there is also a risk of averaging important dynamics if the weights have not been carefully selected. Residual-based or sequential training involves using SARIMA to predict explicit patterns, in particular trend, seasonality, and autocorrelation. Then the residuals are calculated based on the actual values obtained by the SARIMA forecast. The training of a recurrent neural network with an LSTM or BLSTM architecture is performed only on the residuals. That is, the final forecast is the SARIMA forecast and the forecast of the residuals by a deep learning model. The advantages of this approach are a cleaner decomposition, since SARIMA processes linear seasonal patterns and deep learning processes nonlinear, complex, and hidden patterns. The risk of overtraining is also significantly reduced, since the recurrent neural networks only needs to model the residual noise and not the full structure. This approach helps to avoid damping, since SARIMA preserves amplitude and cyclicity. Some disadvantages of the residual-based training approach are the more complex workflow that involves two-stage training. It is also necessary that SARIMA be quite well chosen. However, the limitations considered are insignificant, and the effect that can be achieved is significant. Our study covers a long-term forecast of sea ice extent until 2100. First, let's consider the forecast for the North Hemisphere. A figure on the slide shows the SARIMA model forecast. The model preserves fluctuations well, but has a clearly linear character, which is also observed in previous observations. This means that the forecast of this model can be considered quite reliable. This figure shows the forecast graph of the LSTM model. Although the forecast for the first year is highly accurate and preserves fluctuations, a rapid attenuation is observed for subsequent years. Thus, this model can only be used for short-term forecasts. The forecast of the recurrent neural network with BLSTM architecture demonstrates similar trends to the LSTM model, but the attenuation in this case is not as rapid. However, this model is also not suitable for long-term forecasting. It is obviously that in this case, the use of ensemble models with parallel training will not provide a correct long-term forecast. Therefore, we will perform forecasting using the approach of training deep learning models based on residuals. Figure on the slide shows the long-term forecast of the SARIMA plus LSTM ensemble model. And this one shows the SARIMA plus BLSTM model. The forecast of both models retains the main trends identified by SARIMA, but adjusts the values according to the hidden patterns identified by recurrent neural networks. For implementation in the information system, models were selected that demonstrated high short-term forecast metrics and no long-term forecast deficiencies. Thus, the SARIMA model was selected for the Northern Hemisphere, and the SARIMA plus LSTM ensemble model was selected for the Southern Hemisphere. In the process of developing the web-based information systems, the key previous of ethical and responsible use of artificial intelligence were taken into account in accordance with modern European approaches. Particular attention was paid to the recommendations formulated in the European Union Artificial Intelligence Act, as well as in the documents of the high-level group on AI at the European Commission. Developed information system belongs to the category of low-risk AI systems, as it does not process personal data, does not make decisions that have legal or social consequences for the user, and does not affect the emotional or physical state of the person. The paper implements a basic approach to ensuring transparency. All models used for forecasting, SARIMA, LSTM, BLSTM, are documented and explained within the project. The visualization of trends, seasonality, and residual components allows the user to understand the logic of forecasting in the future. It is planned to introduce mechanisms for interpreting models, so explainable AI, which will improve the transparency of algorithms. As a result of the study and analysis of existing concepts and approaches to the development of XAI predictive models was conducted, on the basis of which the main aspects of the development of a web-based information system for long-term forecasting of the area of the sea ice extent using statistical methods and deep learning methods were determined. A detailed explanation of the features of the application of each of the methods in the context of the use of ensemble models was provided, and the compliance of the developed information system with the ethical and legal aspects of responsible AI was determined. Visualizing and the impacts of climate change on coastal regions allows users to model potential scenarios and better understand potential threats and risks, spurring action on climate change and ensuring the achievement on sustainable development goals in climate action. Thank you for attention. Maybe you have some questions.
Thank you very much, Vitaly, for your fascinating talk. The platform is now open for questions. So, dear colleagues, please, if any. I have a question as one of the scientists here. What are the key trade-offs between the simpler SARIMA model and your more complex ensemble when communicated forecast uncertainty to the public?
As I understand, your question, it means that we have a lot of public models, yes, and we can use it for some forecasting. So we used statistical forecasting models like ARIMA and seasonal ARIMA, and we used residuals-based analysis using LSTM model for to correct some future values on the to reveal some hidden patterns in sea ice. We decided to analyze the BLSTM model. This model in general very rarely used for forecasting task, but now we found some studies which apply BLSTM model for time series forecasting, but not in climate forecasting. So we decided to apply this technique and to compare results.
All right, I understood. Thank you very much. Dear participants, any other questions? All right, that's all the time we have for inquiries. Let's thank the speaker again. And our second presentation is CNNs are explainable domain-specific visual embeddings. Please welcome Zakhar Ostrovsky and his co-authors, Andriy Bioshetskiy and Dmytro Ugrin. Zakhar, the platform is yours.
Hello, everyone. Please tell me whether you see my presentation or not.
The slides are visible. Everything is okay. You can proceed.
One moment. Okay, so do you see it in a full screen mode or as a Google Slides presentation? Because I have two screens and I can't understand what it shows. Zoom.
Full screen is visible. Everything is fine.
Okay. So hello everyone, thank you for joining me today, and my presentation is on the topic CNNs are explainable domain-specific visual embedders. My name is Zakhar Ostrovsky, and I hope you find my research both interesting and useful. So, what is the problem that is addressed in my research? Unmanned aerial vehicles increasingly operate in environments where GPS signals are unreliable or entirely absent. Under such conditions, visual landmarks, distinctive, visually recognizable under various conditions of illumination and altitude objects, identified from onboard camera images, become the sole method for determining UAV location. Thus, by using a set of landmarks for a given area, a road can be planned to a specific point, allowing UAV navigation even without GPS signals, relying solely on environmental image analysis. The existing problems revealed by the literature analysis indicate that there is a limited attention to landmark-based UAV localization methods. Most existing approaches generate descriptors vectors for entire UAV images, matching them against annotated database. However, these descriptors may be sensitive to imaging condition changes and background noise. So the primary purpose of this article is to enhance identifying unique objects in aerial images of urban areas on the Earth's surface, which can potentially serve as a stable landmark for UAV navigation in the absence of GPS signals. The main contribution of this research is a lightweight explainable pipeline that, first, extracts multi-layer objects masked CNN embeddings for buildings without extra training. Second, applies unsupervised outlier detection to create a compact set of distinctive geotagged landmarks. And third, demonstrates substantial visual place recognition gains when queries are restricted to these landmarks. The process consists of the 5 main steps described on the slide. At first, we segment buildings in satellite images to form a database. Then we extract intermediate CNN features from hidden layers for each building. Third, we aggregate the feature maps into a single embedding vector to unify them in a fixed vector with a fixed shape. And then we apply outlier detection to find atypical standout buildings. And finally, we use these buildings as navigational landmarks for UAV in GPS-denied settings. To test our approach, we used the WePair dataset that covers trajectory spanning more than 100 kilometers, and where there are satellite and UAV paired images for the whole trajectory. There are multiple layers, hidden layers of the CNN to select the features from, and there is a couple of aggregation functions to apply. And selecting the best combination of them is not trivial. So we introduced 2 proxy metrics, satellite to satellite and satellite to drone, in order to guide the selection mechanism in a very quick way using best first search. The satellite to satellite metric is based on queries and database, neighboring overlapping satellite crops, and is a single domain, while the satellite to drone is related to queries, being the UAV aircraft views, and the database is satellite imagery. This is multi-domain. We've selected the best combination using these proxy metrics and best first search algorithm, which is described in details in the article. Then we analyzed the obtained embeddings qualitatively using the dimensionality reduction algorithm as visualized on the slide. Black points represent landmark buildings, while blue points represent typical buildings. We used two-dimensionality reduction algorithm, PCA, which is known for capturing linear relationships in data, and TSNE, which captures nonlinear relationships. As we can see, both plots show a clear distinction, a clear cluster of typical and landmark buildings, indicating the high quality of our embeddings, so that landmarks are distinctive both in linear and non-linear sense. We made a more detailed analysis of the obtained embedding space by making a focused inspection of some points. And on this slide, you can see the visualization of buildings from the outlier cluster and from the typical buildings cluster. As you can see, the buildings from the outlier cluster are large and distinctive. And what's important, the same building captured on different images is grouped in a small subcluster, meaning that the embeddings are robust to the changes of views and greatly identify the same building, while the small buildings which cannot serve as reliable landmarks naturally appear in the typical buildings cluster. And the same is proved by analyzing the TSNE plot as shown on this slide. Interestingly, the embeddings capture even semantics like partial presence of the buildings, as you can see in the typical buildings cluster. These buildings appear at the edge of the photo and are not fully visible within the view, and they both cluster in the same subcluster. To measure our embeddings qualitatively, we introduced the per building annotations because the original dataset does not contain building to building annotation. So we manually annotated a subset of buildings from both satellite and the corresponding drone images, and tested our retrieval on this subset. And as you can see, the retrieval accuracy of landmark buildings has a substantially larger retrieval accuracy compared to the retrieval of typical buildings. We also studied the edge cases to prove the robustness of our algorithm and to find out its limitation. In the first row of the slide, the UAV captured buildings for which a match is searched from the satellite-based building database is shown. The second row presents the corresponding satellite-based reference building, the ground truth one. The subsequent rows illustrate the most similar buildings based on altitude distance in embedding space. For compactness, we show only the top two most similar samples. So the cases A and B demonstrate robustness to YOLO V11 segmentation errors, because in these cases, it segmented the same building twice by also including another building in the second case, and still it was possible to retrieve the correct building. The case C proves the robustness to more than 90-degree rotations between the query image and the reference image. In case D, the retrieval failed, and it emphasizes the importance of selecting unique landmark buildings to ensure retrieval accuracy. As you can see that although the retrieved images are visually similar, or orange prolonged buildings, this is not the one we actually searched for. So here are the limitations of our work outlined. First, the experimental validation in this study was conducted within an urban environment using buildings as landmarks. Both satellite and UAV images were captured during daylight from the same vertical top-down perspective. Second, importantly, the specific set of landmark objects for a given set of satellite images depends significantly on the particular convolutional neural network used. Different neural networks might segment the same image differently, potentially failing to identify buildings or merging multiple adjacent buildings into a single segment. Additionally, object embeddings generated by these networks may differ, resulting in variations in the final landmark object set. The calculation of recall at 1 and recall at 5 metrics for matching accuracy between UAV and satellite images required human labeling for search results. Due to the time-intensive nature of this task, the test dataset size was limited to 200 unique buildings. The future work includes the following directions for improvement.
Dear Zahar, I very apologize for interrupting, but please remember about our timetable.
So we can extend to other types of objects. We can try to use contrastive learning method to increase the distinctness of the buildings, and we can use a more adaptive and flexible clusterization and outlier selection algorithm other than isolation forest. This has shown a unique perspective to address the landmark selection for UAV navigation, and showed that showed its potential for practical applications with a significant increase in retrieval accuracy, and outlined the future direction. Thank you for the attention. I am open to your questions.
Thank you very much, Zahar, for your wonderful speech. Dear colleagues, the platform is now open for your questions. I would like to ask one. So, Zahar, your landmark-based approach works well in urban areas, as we can see from the presentation. But how do you envision it performing in less structured environments like rural landscapes?
My approach requires distinctive objects to be present in the view. It should be adapted to the landscapes where there are no regular structures, and although the core idea of identifying outliers in the embedding space I envision it to be relevant. I also think that what is selected as to form embedding will differ. For instance, if there is a prolonged part of the landscape with no regular structures, but we should search for some other patterns that distinct it, and I think that may be the change of the terrain structure within the flight. So we cannot focus on distinctive object, but we can focus on the changes in the terrain surface structure within the flight. So, for example, it may capture, it's like taking differences between the sequential images and identifying the changes. For example, when a field with one crops growing on it subsequently changes to the field with another crops growing in it. And we can identify that something has changed at the intersection of these fields by taking the difference of the for example, the embeddings of their landscapes. And that will be some distinctive feature we can try to use for orientation. But within, because when there is nothing outstanding in our view, then we cannot take it for the orientation.
Okay, so one more thing, in short, to clarify, as I understood correctly, your approach can be applied to rural areas. Or not really?
Yes, but it should be adapted with the objects. I mean that we should build not the embeddings of the objects, but the embeddings of the, for example, the surface texture of this landscape.
Okay, understood. So please keep this in mind, because in your future seminars, I'm pretty sure this question will be raised again. Dear fellows, any other questions? If none, then that's all for this talk. Let's thank the speaker one more time. Thank you, Zahar. Next up, we have a presentation on neural network detection of digital fatigue and burnout with interpretable thematic segmentation. This work is by Alexander Mazurets and a team including Roman Vit, Marina Molchanova, Olena Subko, Adam Verbitsky, and Dmitry Chuvachenko. Please, dear Roman, take the platform.
Hi, everyone. Can you see my screen now?
Yes, the presentation is visible in a very good way. You may proceed.
Okay, so today I would like to tell you about our work, neural network detection of digital fatigue and burnout with interpretable thematic segmentation. So with the rise of remote work, digital communication and online education, more and more people are experiencing digital fatigue and burnout. And the relevance of addressing digital fatigue is also emphasized within the framework of the United Nations Sustainable Development Goals, SDG 3 and SDG 8, it's mental health and well-being and decent work and sustainable economic growth. So the development of interpretable neural network approaches to monitoring digital fatigue contributes to the creation of healthier, more sustainable and human-centered digital ecosystems. So the aim is to develop and test a neural network interpretable approach to automated detection of digital fatigue and professional burnout through thematic segmentation of text messages and analysis of communication objects, which allows to detect hidden patterns of psycho-emotional exhaustion in the digital environment. The main contributions are the new multi-stage framework for detecting digital fatigue is proposed, the neural network detection of digital fatigue and burnout using thematic segmentation and communication object analysis method is implemented, which allows for targeted assessment of fatigue within the content of communication. The multi-indicator fatigue assessment model is developed, which allows for calculating both localized and aggregated levels of digital fatigue across all user profiles. And the visualization module is created to interpret user-specific digital fatigue maps, which will allow for identifying problematic communication segments. So detecting digital fatigue through text is a bit complicated because linguistic themes do not always reflect the author's real psycho-emotional state. And presence of words about fatigue or negativity does not necessarily indicate actual digital fatigue. So text may express emotional exhaustion without digital context or mention fatigue only descriptively. So it's essential to distinguish thematic content from latent psychological markers of human condition. Interpretable method and software must be developed to evaluate its effectiveness. So on this slide, you can see method design. Probably I want to move this. Yeah, probably would leave as it is. So here you can see in like first column is input data. Here we have many entries of author profile, and this block can include posts, comments, notes, and so on. Then we have 3 stages. First stage is thematic classification. So here we have communication segments, and here we use LDA algorithms, which assigns each entry to one of identified topics. Then second stage, here we have target objects of communication. Here we use multiple methods to extract these objects. We use TF, IDF, Yaki, and dispersive estimation along with NER and lemmatization to ensure accuracy and conceptual integrity. And on third stage, we perform a classification using a BART model, which creates contextualized vector representations of text. And as output data, we receive a digital fatigue map by profile, and like for each segment, and specifically by profile. Here you can see our experimental data sets. The first one is Khmelnytskyi Walker's burnout tweets dataset that contains tweets from Khmelnytskyi Walker's. And second one is mental health social media dataset from Kaggle, corpus of English language tweets. So one was used as a training data, and second one is used as a testing data. And also on the right side, you can see experiment and setup description. So here you can see on the left side metrics and results, and on the right side also you can see confusion matrix. So confusion matrix shows that the result demonstrate balance between two classes, the presence of digital fatigue and its absence. So model shows relatively equal performance for both cases. So it can accurately distinguish both categories. And in general, the illustrative materials provided confirm the correctness of the proposed approach, since this table shows the category with digital burnout. So more than 95% were classified correctly, and only 5% were in within the statistical error. And on the right side, you can see a map of digital fatigue and burnout by communication segments built by mental health social media dataset. So on the left side, we can see topic 1, which is related to higher burnout rate, and topic 2 is related to much less burnout rate. Yeah, and in conclusion, I would say that the paper introduces a new approach to automated detection of digital fatigue and professional burnout based on text analysis using interpretable semantic segmentation, target object identification, and neural network classification with BERT architecture. Method enables multi-level assessment of cognitive and emotional load in digital environments, ensuring contextual and semantic sensitivity to signs of digital fatigue. Neural network model achieved these results, which are shown. I mean, accuracy, precision, recall, and validation data. And unlike traditional global text or metadata-based models, the approach applies semantic classification, isolating semantic communication segments for contextual interpretation. So far, the analysis within segments identifies target communication objects, improving contextual understanding of digital behavior. And a formalized multi-level model of digital fatigue assessment is proposed, covering topic posts and user profile levels, enabling detection of both local overload points and overall fatigue. That's it. Thank you for your attention.
I'm grateful to Roman for his awesome presentation. Dear participants, the floor is now open for any inquiries. Okay, if none questions for now, I would like to clarify one thing. Please, Roman, tell me, what are the main challenges in adapting your model to capture the cultural and linguistic nonsense of digital fatigue in other languages?
Yeah, as of now, our network has been trained only on English language. So it mostly uses some structures that are common for digital fatigue and burnout, which is relevant to Western countries. But it also can be adapted and trained for other languages, such as Ukrainian, for example. So I think that in further investigation we can definitely cover that topic and perform this adaptation to obtain results for different cultures and different languages.
Okay, thank you very much. I understood. Dear participants, any other inquiries?
Okay, thank you for the question and for time.
Great. So if none, that's all for this talk. I thank Roman once again. Thank you. And for our final presentation in this session, we have an explainable artificial intelligence approach for detecting network attacks. The authors are Dmytro Demyshchuk, Andrei Sverstyuk, Yuri Klots, Natalia Petliak, and Viratik Tova. I wish I could say welcome, but unfortunately, due to the electricity shortages, the author messaged me that they are unable to make a presentation right now. Fortunately, we have prepared for such a condition videos, and right now I'm going to open it. Video. Oh, just give me a second. Okay, partial screen. Let it be partial screen. Partial screen. Now we can see the video, and I will start it right now. Just give a second. Audio. Right now we need to change the audio for it. Okay, in this case, I will open the video from my second device. Or okay, sharing the video. Dear participants who are listening to me right now, please can you confirm that the sound can be heard?
No sound.
No. Okay, got it.
While you share a video, you can check the box share audio too. On the screen, share a video in Zoom.
Sure. Share audio, you mean the one sharing screen? Share sound?
If you start share in the window for select window for share, also in down check share audio.
Got it. Share sound. Yeah, I see share sound. Okay, share.
The machine learning models.
What about now?
It's good. Let me introduce my article, An Explainable Artificial Intelligence Approach for Detecting Network Attacks. The research aims to build machine learning models that can detect network attacks accurately while keeping false alarms low. It focuses on making the system fast, scalable, and easy to understand using explainable AI. The main idea to combine machine learning models with explainable AI methods to improve detection accuracy and make IDS APS detection more transparent. We used the UNCVNB15 dataset. It mixed normal traffic with bad traffic attacks. The data has 38 details about the network, the time, and data packets. Each entry is one network session. We use it to check if traffic is normal or bad. The dataset has many attack types, like DDoS, exploits, and worms. This is good for testing security system. This slide shows a distribution of classes in the dataset using a logarithmic scale on the y-axis. To check how well our models work, we used common metrics often applied in IDS, IPS research. Log loss is a measure used to check models. It is good for tasks with two classes like yes, no, or attack normal. It checks if the model confidence is correct. If the model is very sure and correct, the log loss score is low. This is good. If a model is very sure but wrong, the score is very high, but is bad. For example, a model say 99% sure that is an attack, but it is really normal traffic. The log loss score will be very bad. So log checks two things. Is the model's answer right or wrong? Now sure, confident, the model about it answer. This is very useful for security and finding network attacks. We need to know if a model is both correct and confident. For every model, we made confusion matrix and calculated matrix. The neural network was most accurate, so we checking it more. We made precision recall, ROC, and F1 curves. We also used LIME and permutation importance to help explain the model precision. Here are the main settings we used: random forest, XGBoost, MLP. For all models, we set random state 42. This means we can run the code again and get the same result. This slide shows the confusion matrices for this and three models. A comparative analysis demonstrate differences in classification quality between the three methods considered. Random forest demonstrated the worst result among the algorithm considers that the overall accuracy is 0.93, and the average precision and recall are significantly lower compared to other models, indicating a higher number of classification. The Xbox model shows a much better balance, achieving an accuracy of 0.94 and high precision 0.98 for each attacks, and recall 0.96 for normal traffic values. However, its log loss is 0.11, indicating a lower confidence in predictions compared to MLP. The MLP neural network demonstrates the highest overall accuracy of 0.95 and the lowest log loss 0.07, which means more stable and confident predictions. Also, the F1 score of both classes in MLP exceeds the corresponding indicators of other algorithms. And the J-means value confirms the balance of classification. We look at a graph to check the MLP model's work. F1 score graph with graph shows that the best threshold for the model is 0.54. These settings give the best balance to find an attacks. Precision recall curve with graph score was very high, 0.99. This means the model is very accurate and help avoid too many false alarms. Rock curve, this graph score was also very high, 0.99. With this almost perfect score, it means model is great and separating normal traffic from bad traffic. It's important to understand how the machine learning model make its decisions. This is a big task in cyber defense. Then experts can see why a model thinks something is an attack. They can trust the system more. To explain how our MLP model works, we use two explainable AI methods, permutation, future, and importance, and line. Slide shows an example of a local prediction explanation for sample 45078 classified as attack. We checked which features made the model decide attack. To future, source time to leave was the most important. It had a big effects over 0.21 and strongly pushed the model to choose attack. Other attack features and swings were also important for finding attacks. And on the other hand, some features point to normal traffic. Normal features and debates were used, but the effect was much smaller. This checks show the model looks at many different things to make a choice. It's used time details, protocol details, and data states. To check all features in general, we used the permutation future importance method. The results are on slide 10. The lab environment was built on a KVM hypervisor, allowing the creation of an isolated network for realistic IDS testing. The setup included the external internet segments and an internal protect networks. Inside the virtual lab, several systems worked together to simulate a real company network. Parrot Security OS and Kali Linux were used for attack simulation and penetration testing. This configuration closely mirrored real-world conditionals. The IDS placed in the internal segment monitored and classified traffic using an MLP model along this signature and anomaly detection method, allow a full evaluation of IDS performance. The study shows that combining machine learning, this explainable AI improves both the accuracy and transparency to intrusion detection system. The models Random Forest, XGBoost, and MLP were tested with MLP, achieved the best result accuracy 0.95, log loss 0.07, AP is 0.99 and AUC 0.99. Using explainable AI helped explain models detection truth line and permutation future importance, highlighting K-networks features such as TTL, connection statistic, and data volumes. This increases expert trust supported IDS policy tuning. Testing in a realistic KVM-based lab confirmed the effectiveness to proposed approach. Thank you for your attention.
We thank the authors for the interesting speech prepared in advance. Dear participant, the ground is now open for your questions because one of the authors is available right now. Well, actually, I have one. Dear Dr. Klotz, could you please clarify how do you anticipate your model will perform against modern zero-day attacks not present in the 2015 dataset? And can the explainable AI methods help detect such novel threats?
Thank you for your question. Are you listening me?
Yeah, we can hear you.
In most cases, modern zero-day attacks are not entirely unique, as they combine previously known or similar behavior patterns, such as request sequences, tuning intervals, statistical characters, and many others. A specified exploit or vulnerability may be new. The system behavior during attack often reproduces features characters of other already known attack classes, such as DOS, brute force, or many other. Machine learning models would analyze behavior and statistical characters of network traffic are not always able to fully detect zero-day attack, but they can potentially identify then truth similar patterns even when such examples as absent from the training dataset.
Okay, if that's it, that I'm quite satisfied with the answer. Thank you very much, Dr. Klotz. Dear colleagues, any other inquiries or any remarks? If none, then thank you very much again.
Thank you.
So this talk and these questions would conclude our first session on explainable AI. A big thank you to all our speakers for getting us off to a strong start. We are going straight by the timeline. So another session will start in 10 to 15 minutes at 10:30 a.m. See you in 10 to 15 minutes. All right, dear friends, welcome back. I hope you can hear me well right now. And I hope you had a good break. We now move to our second session, focusing on AI ethic and governance. We have 3 presentations in this block, according to our program. Our first talk of this session is titled A Method for Synthesizing System Architecture for IT Infrastructure Resistant to Social Engineering Attacks. This research is presented by Cyril Lysenko and his colleagues Alexander Bokhenko, Thomas Sokor, Olga Tamanyuk, Nadia Lysenko, and Jiri Balay. Professor Lysenko is joining us right now, thankfully. So, Professor Lysenko, the floor is yours. If you're ready, you can proceed with your presentation.
Dear colleagues, hello. My pardon. My colleague will be making this presentation. He is connecting right now. 1 second, please. Alexander will be presenter.
Got it. Well, the presentation is clearly visible, so dear Alexander, you can proceed.
Good day. My name is Alexander. Today I am presenting you our work on methods for synthesizing systems architecture for its infrastructure resistant to social engineering attacks. Second, please. We will start with the motivation, move to the core idea of our research, then detail the proposed solution and conclude with the results and summary. So the motivation. Traditional defense like firewalls are effective against deception targeting human behavior. We see a growing volume and diversity of attacks. The limitation of known methods are clear. Rule-based systems can't recognize novel attacks, and most models rely on static fetches and cannot integrate data from multiple sources at once. This leads to the need for advanced approaches. We believe that hierarchical multi-agent architectures and reinforcement learning are key to optimizing decisions under incomplete information and adapting to new tactics. The core idea of our research is to propose a method for synthesizing an architecture based on an hierarchical multi-agent system using reinforcement learning. The goal is to build a system capable of detecting attacks through the interaction of specialized components. At its core is an agent that is coordination with an attack classifier formulates policy and directs the collection of the technical and contextual features such as text, simulation, or networks parameters. Our method uses a two-level classifier. At level 1, it looks for general things of social engineering. At level 2, it refines the assessment to identify the specific type and tactic of the attack. The architecture has two key agent types. The decision agent coordinates the overall policy and makes the final verdict. It is supported by the service agents, which perform specialized analysis of specific data like email, web, or voice. The system also supposed by a connector monitor components, a simulation engineer component, and an interaction manager component. Moving to the solution, our hierarchical constructor consists of a high-level decision agent and low-level service agents. In each cycle, the main agent receives the current state of the improvement, which is the set of all collected attacks indicators. Each service agent has its own set of actions. After it completes a subtask, the decision agent received the results and we calculate the accumulated rewards for that cycle. On this slide is a formula by which we calculate the accumulated rewards. The essence is to calculate it differently depending on whether the action was delegated to a service agent. A top line which includes discounting of it was a final classification. To train the decision agent, we calculate it's okay. To train the decision agent, we calculate the loss function. Its purpose is to minimize the error, the squared difference between the exit reward and the current estimate. Similarly, we calculate the loss function for each service agent. It works the same way, but it's based in its local policy and its own enterprise buffer. A key innovation in the use of entropy, we calculate the initial entropy or uncertainty for both the decision agents and the service agents. In practice, we calculate the entropy before an action as the entropy after the action. The difference between these values becomes the basic to the reward. In short, we reward the system for recurring uncertainty. Here we see how we calculate the rewards. Based on this difference, we normalize it against the initial value and use the max operator to ensure the reward is not negative. The internal reward for service angels is calculated from two parts: the entropy reduction reward and additional value n. N is positive is the query was useful and negative is the query was reductant. Similarly, we calculate the external reward for the decision agent. N is positive if the final decision is correct, and negative if the action was a repeat with penalizes reductant queries. To manage which features and analyze, we calculate the current probability distribution of theta manifestations based on the probabilities of attack classes. Finally, we calculate the final action By combining this probability distribution, which the Q values, the argmax function determines which actions the agent should focus on. Let's move to the implementation. We evaluated our architectures across 4 aspects: accuracy, efficiency, generalization, and ablation analysis. We used a corpus 1000 samples for the results. We used priors from a knowledge graph and compared our system against baselines, including a flat DNN model.
Dear Alexander, I very apologize for interrupting, but please keep in mind that we have strict timelines, so a bit intensify your speech. Thank you.
Okay. So, to summarize the experience states, we implemented a system with 1 decision agent and 2 service agents. We integrated our entropy normalized reward function and conducted an ablation analysis to evaluate the contribution of the hierarchy. And most importantly, the results. This table shows a direct combination of our full hierarchical system against the non-hierarchical model. Our system demonstrates significantly higher metrics and low false positive rate. But the K is efficiently, we only need 3.2 actions per sample compared to 5.7 for the flat model. In conclusion, we have developed a new method for synthesizing a hierarchical multi-agent architecture. Our system outperforms non-hierarchical models on all metrics. We successfully reduced the number of required action by 44%. In practice, this means lower latency and better adaptability. It can serve as a universal solution for building IT infrastructure to protect against social engineering. Thank you for your attention.
Thank you, Alexander, for your wonderful talk. Dear friends, you may now ask any questions if you have some. If none from you, then I have a question. I wonder, how could your system's explanations be used to educate end users on why a message is suspicious, improving their long-term security awareness? Would you please clarify on that?
The key result of our work is not to present a silver bullet, but to demonstrate a path of a much more efficient system. Our focus was on providing that our method provides a fundamental improvement of efficiently speciality, 44 reduction in actions, which creates a strong foundation for future explanation like that.
Okay, that's clear to me. Thank you very much. Dear colleagues, any other questions? If none, then thank you, Alexander, and thank you, Professor Lysenko, again for this great work. We thank the speaker. Next, we will hear about a linear ensemble model with winner takes all aggregation strategy for improved small data classification. The authors are Ivan Izonin, Roman Tkachenko, Serhiy Chesanov, Yaroslav Tolstyak, and Miroslav Stupnitsky. Dear Dr. Ivan, if you can hear me, please, the floor is yours.
Thank you. Thank you. Dear colleagues, first of all, thank you very much for organizing such important for today event. I would like to present our results, a linear ensemble model with winner takes all aggregation strategy for improved small data classification. Author is Ivan Izonin, Roman Tkachenko, Serhiy Chesanov, Yaroslav Tolstyak, and Miroslav Stupnitsky. I am Ivan Izonin, an associated professor at the Department of Artificial Intelligence of Lviv Polytechnic National University, and also researcher at the University College London, United Kingdom. I obtained PhD degree in System and Means of Artificial Intelligence in 2016. Also, I have a bachelor and master degree in economic cybernetics and a bachelor and master degree in computer science. Currently, in Lviv Polytechnic National University, I am working at a high-speed computational intelligence lab. The lab head is Professor Roman Tkachenko. Our lab focused on the developing high-speed computational intelligence mean and narrow fuzzy system for different purposes. My area is small data analysis. In medicine, in biomedical engineering, in different areas, we have some problem with small data. When we have some ethical restriction, financial restriction, time restriction, and other to collect enough data for solve some applied task by machine learning algorithms. When we use such data set and try to apply machine learning algorithms, we have a lot of problems. Some of them you can see on the slides. It's overfitting problems, influence of noise, missing value outliers, limited ability to generalize, small validation sample when we use iterative models, and others. And in our work, we try to develop some linear methods, some simple, interpretable methods that provide results with higher accuracy. Therefore, the objective of this study is to improve the effectiveness of classification in small data scenarios by developing a linear ensemble model with data normalization and winner-takes-all aggregation strategy. According to existing approaches, there are three main classes of methods that working with small data. First of all, it's a kernel method that can provide a better accuracy than linear methods, but in this case, we should have enough data, enough examples in our data set. When we haven't it, we can use data augmentation techniques, different techniques, but when we use it, the medical doctors don't trust such solution because we create synthetic data. And this is not very common use approach in medical domain when we want to apply this approach in practice. And the second class is ensemble learning, when we try to combine several machine learning models or artificial neural network to obtain a better decision. In our research, we use this class of methods, ensemble learning, but we try to create an ensemble from the linear models to obtain a better results. In this case, we solve the classification task, and we propose an ensemble from linear regressors to solve this task. Our ensemble work in two modes. First, it's a training modes. We have our data sets. First step is splitting the available data sets into the training and test sets. We create separate training subsets, and the number of such subsets corresponds to the number of classes in our classification task. Each subset has the same size but a different target attribute constructed using equation 1. Then we normalize our independent attributes using column-wise equation 2 and row-wise methods equation 2. Then train each our weak regressor in our ensemble and saving the minimum and maximum prediction value for each weak regressors. In the application mode, we have the vector when we should predict the target attribute. We doing the same sequential normalization row-wise and column-wise for this vector, then apply this vector to each our weak regressors. Then we normalize output of each regressors and try to find the best solution using equation 1. As a result, the class with the higher normalized prediction value is chosen as a result of our ensemble. The simplified flowchart for the case of binary classification task you can see on the slide. Modeling. Modeling was conducted to solve the real-world task to predict mortality among the multiply trauma patients. This dataset was collected by the specialist from Kharkiv City Clinical Emergency Hospital, our Professor Mechanikov. We have 73 vectors and 56 independent attributes. Distribution of classes you can see on the slide, 31 for fatal cases and 42 for non-fatal cases. Data was anonymized, it hasn't missing value or outliers. Therefore, it's ready for detailed analysis. For our developed linear ensemble model, we used different linear machine learning algorithms as weak regressors. We called it different algorithms. Algorithm 1, when we use neural-like structure of the successive geometric transformation model as a weak regressor for each member of our ensemble. Algorithm 2, it's as a support vector regression with linear kernel, and algorithm 3, it's a rich regression. In the table, you can see the different performance indicators for in the train and test mode for different algorithms. As you can see, in most cases, we obtain a very high accuracy, taking into account the small number of observation and a lot of independent attributes. We compare our results in both ways. First of all, we compare our ensemble model with the weak regressor that creates such ensemble. And in the diagram, you can see that then in most cases, we obtain a higher accuracy than a linear model. Also, we compare our results with two existing nonlinear ensembles, ADA boost and gradient boosting, and as a result, we obtain a higher accuracy than these methods. Future research will be conducted in the direction to adapt this ensemble to multi-class classification task when we use also weak regressors to solve it, linear regressors. The main advantage of such approach is we use linear models, then we have interpretable solution. We obtain a higher accuracy, not so high in comparison with existing linear methods, but higher than they provide. And we obtain, we have much less computational complexity in comparison with nonlinear methods. Thank you for your attention.
Thank you very much, Dr. Ivan, for this wonderful speech. Dear colleagues, Please, I welcome your questions, if any. Of course, I would like to ask something. So, DA1, your work on small data is highly relevant. Could you please elaborate on why the proposed two-stage normalization process is so effective for improving your ensemble performance?
Thank you. In most cases, all of us used the classical normalization methods, column-wise or row-wise, one of the methods. But when we use a vector scalar, it provides the information about the dependencies of independent attribute in each vector. It's very important for medical and biomedical fields because classical approach didn't take into account the such dependencies. But such dependencies is very important and very informative for machine learning algorithms. Therefore, we use this approach and it helps us to improve the accuracy. Thank you.
Okay, understood. I'm very pleased with the answer and quite satisfied with that. Dear colleagues, any other inquiries or remarks? If none, we should I should say thank you, Dr. Izonin, one more time for your participation and your kind words. Let's proceed to our final presentation for this session, which is an approach to identifying functional and non-functional requirements in IT project management using deep learning models. This paper is by Ruslan Bahri, Tetiana Skripnik, Bogdan Romanov, Yelena Zaitseva, and Huda L. Boysi and Volodymyr Litvinenko. Please, dear authors, the floor is yours. Dear
Так, я
Bogdan,
включаюсь.
yep, but please pay attention to our
Окей.
working language, which is English. Okay, the platform is yours. The presentation is clearly visible. You can continue.
So today's presentation is an approach to identifying functional and non-functional requirements in IT project management and using deep learning models. This presentation covers the general state of art, research methodology, results, and conclusions. So, first of all, motivation, accurate representation of functional and non-functional requirements can be very important for the process of software development, and doing so manually can be very labor intensive and prone to human error. And using automated methods for this specific task can greatly increase the speed, accuracy, and objectivity. And what is also important, it aligns with Sustainable Development Goal number 9, which is industry development and infrastructure, by creating new effective tools for the process of software development and software engineering. What is available when we talk about state of art? Modern approaches already use large language models such as BERT or RoBERTa to achieve state-of-art accuracy in supervised classification. However, there is a specific problem for unsupervised methods, which can be called a semantic gap. The general A point of this problem is that models are generally trained on unspecified datasets that can then fail to capture specific semantics of software engineering. So they can lack understanding of specific terms like performance, security, etc. Because these terms can have different meanings depending on context. So our goal is to improve the quality of unsupervised requirement classification by applying a special domain adaptation on our pre-trained models. And to do that, we have created a general roadmap. So we have to compare a clustering between and after fine-tuning. We compare different layers and we compare different methods of fine-tuning to find out which is more appropriate and provides more accurate results. So as for the actual used methods and components, we used Roberta base as our base model. We used two fine-tuning techniques, which is standard fine-tuning by binary classification task, contrastive learning, and we used two separate clustering algorithms, which k-means specifically tuned for binary classification, and HDB scans, which has a special ability to identify certain points as outliers. Our general workflow for every clustering experiment, we take our text to generate multi-layer vector representations using our large language model. This can also be called embeddings. Then we unify this into singular vector formation using either pooling or selecting a classification token. Then we apply the clustering algorithm itself to separate our data into specific clusters. And as the last step, we evaluate our clustering accuracy to see how well we managed to separate functional and non-functional requirements. As for the outputs of the model itself, we have specifically for Roberta 12 hidden states or 12 layers with specific sizes. As for the datasets, we used two separate datasets. We used Promise EXP dataset in its unchanged form, and we used FR and FR dataset after balancing it for 2000 requirements, 1000 requirements per class, and the ground truth labels were used exclusively for the evaluation in the end. They were not used during the clustering itself. So very first, this is in a way benchmark the base model itself before any pre-training, before fine-tuning. It fails very badly. It's barely better than random classifier. Then this is after applying standard fine-tuning. Our F1 score has significantly increased. And if we look at the graph itself, we can see that there is now much more clear separation between classes. Next, we evaluated different layers after the first fine-tuning. As you can see, the general trend is that using the latest layer gives better accuracy, and what we have also identified is that using complex combinations, for example, last 4 layers did not give any significant additional benefit. As for contrastive learning, it has similarly achieved a much greater F1 score. However, the graph itself, the chart can show a much clearer distinction between two classes, and most of the outliers are concentrated in between those two classes, which means that we may have correctly identified certain ambiguous requirements. So as for the general conclusion, we have proven that Dalmatian adaptation can be used to overcome the problem of semantic gap by introducing greater levels of specialization. Our used approach have greatly increased performance compared to the standard model, and our achieved levels of F1 score are very close to the fully supervised upper bound, which means it can be practically implemented as an alternative for supervised methods. And it can be also used as a potential practical path for automating the requirement analysis without needing very large labeled datasets. As for contrastive learning itself, it has shown to create much more clear separation between classes, despite having a slightly lesser accuracy. However, this is within limit of statistical error, so it can be used as a very effective alternative to other forms of adaptation. And the last layer was identified as the most optimal representation. Well, this we have already said. And what are our limitations? We have used only model Roberta base as our base large language model architecture, and we relied on English language or specifically within our scope. What can be done in the future is using different types of domain adaptation and different architectures of large language models, maybe not specifically Roberta, but something different. Thank you for attention.
I'm sincerely grateful to Roman for his participation in this event and excellent presentation. Thank you, Roman, once again. Dear colleagues, the floor is now open for your questions. Okay, yeah, Alexei.
Hello, thanks, Bogdan, for interesting speech. I have some simple question. Why you used this approach, and you have some difficulties with your studies deep learning models. Thanks.
This approach was chosen mainly because there was an initial problem which, as identified in the base model, it had very poor accuracy and separation between classes.
Okay, thank you very much, Alexei, for your insightful question, and Bogdan, for your excellent answer. Any other questions, colleagues? All right, So if none, then we shall proceed. Because that's all for this talk. Let's thank the speaker again. Thank you, Roman. All right. Thank you to all our speakers in the second session. We will have another short 15 minutes coffee break, or even 20-minute coffee break, because our next session starts at 11:30 by Kiev. So please be back in the seats or in front of your monitors in approximately 20 minutes for our third session. It will be intriguing as well. If any questions or remarks, please ask them right now, or you can leave the message in the Zoom chat. See you in 20 minutes. All right, dear colleagues, welcome back. Our third session is dedicated to sustainable development goals, putting the core theme of our workshop into practice. We have 4 presentations scheduled. First up is AutoML, PyCaret, and SHARP Explainable AI for ECG signal classification based on amplitude variability. Please welcome the authors of this work, Dmytro Tymощuk, Irina Didich, Andrei Sverstyuk, and Yuri Khmelnytskyi.
I'm trying to share my screen. Can you see my slides? I'm scrolling now.
Yeah, the slides are visible.
Okay.
Dear Yuri, the platform is yours.
Let me start. Okay. So good morning. I'm pleased to share our study on AutoML, PyCaret, and SHARP Explainable AI for electrocardiogram signal classification based on amplitude variability. Our work focuses on relatively understudied aspect of ECG analysis, the amplitude variability of characteristic cardiac waves. We've developed an information technology that integrates the PyCaret AutoML framework with SHARP analysis to create a diagnostic system that is not only highly accurate, but also transparent and interpretable. This combination is particularly important in medical applications, where understanding why a model makes certain decisions is just as crucial as accuracy of those decisions themselves. Cardiovascular disease remains the leading cause of mortality globally, accounting for 17.9 million deaths each year, according to the World Health Organization. Electrocardiography as non-invasive method plays a fundamental role in cardiac diagnostic, yet traditional approaches of ECG analysis have predominantly focused on temporal parameters such as RR intervals and heart rate variability, as well as the morphological characteristics of individual cardiac cycles. However, there exists a significant research gap, which we aim to address: the cycle-to-cycle amplitude variability of characteristics ECG wave, specifically the P, Q, R, S, and T waves, has remained insufficiently studied despite its considerable potential. We believe what these diagnostic changes in amplitude values between successive cardiac cycles may serve as sensitive indicators of early pathological alternation in the cardiovascular system, potentially revealing conditions before they manifest clinically. This gap in the literature, combined with the critical need for improved early detection methods, forms the foundation of our investigation. Our research aims to develop an information technology for cardiovascular disease diagnosis based on ECG amplitude variability. Specifically, we sought to validate amplitude variability as reliable diagnostic marker, apply AutoML with PyCaret to identify optimal classification algorithms, ensure transparency and interpretability through SHARP analysis, and achieve accuracy compatible or exceeding current methods. These objectives emphasize not only accuracy, but also clinical trustworthiness and practical applicability. To address this challenge, we designed a methodology which integrates well-established clinical data sources with modern machine learning techniques. Our starting point was the PhysioNet repository, which contains over 45,000 patient ECG recordings. From this large resource, we proceed and curated a dataset of 651 representative samples suitable for our analysis. The next step was feature extraction. Rather than relying on a raw signal alone,
we focused on quantifying amplitude variability through 10 statistical descriptors, including measures of central tendency, dispersion, and distribution shape. These descriptors capture subtle fluctuation between P, Q, R, S, and T waves, what may hold diagnostic value. For classification, we defined 4 clinically meaningful categories. Normal ECG with pacemaker activity, arrhythmias, and morphological abnormalities such as myocardial infarction scars or conducting blocks. This structure allowed us to test whether amplitude variability could efficiently distinguish between diverse cardiac conditions. To capture the diagnostic potential of amplitude variability, we relied on using statistical descriptors as a measure of our classical model. Mean, median, and may describe central tendency, with the median robust of outliers and the mode highlighting recurring patterns. Standard deviation and variance measured dispersions. Kurtosis indicates the peakness or flatness of the distribution, while skewness measures its asymmetry. As well, we see later in our SHAP analysis, these shape indicators emerge as among the most influential features for classification decisions. Together, these features provide a comprehensive statistical fingerprint of cardiac amplitude variability. We used PyCard AutoML to compare algorithms under identical conditions, ensuring fair and reproductive evaluation. Ensemble methods such as random forest, extra trees, CAD boost, XGBoost, and light GBM all achieved over 90% accuracy and area under curve over 0.94, confirming the diagnostic value and amplitude variability. Random forest emerged as the most balanced model with accuracy over 91% and area under curve over 0.94. Probability calibration further improved reliability, making it the optimal choice and the basis for the subsequent SHAP explainability analysis. The calibrated random forest model showed strong performance across all classes with area under curve values above 0.96. The confusion matrix highlight high accuracy, 95 for normal cases, near 100 for pacemaker patients, approximately 92 for arrhythmias, and over 89 for morphological abnormalities. ROC curves, receive operating characteristic curves, confirm excellent discrimination with area under curve over 0.94 with one VSO strategy. To ensure clinical trust, we used SHAP, shapely additive explanations, to interpret our model. SHAP offers global insights into key features, local explanation for individual predictions, and transparency for clinicians. Skewness and kurtosis as indicators of distribution shape were the most influential feature, highlighting their diagnostic value. Other important features included minimum, range, and maximum values, with standard deviation and central tendency playing smaller roles. This confirms our feature selection and reveals which aspects of amplitude variability best signal cardiac conditions. Beyond technical results, our work emphasizes ethics, transparency, and societal impact. SHAP analysis ensures explainability, fostering clinical trust, while open physionet data guarantees reproducibility. Aligned with Sustainable Development Goal number 3, our approach enables early detection of cardiovascular diseases, is accessible through AutoML, and remains efficient on standard ECG equipment, making it suitable even for resource-limited settings. Together, these qualities support equitable and trustworthy healthcare. We acknowledge a key limitation before clinical deployment. Our data set of 651 samples is relatively modest, requiring validation or larger diverse cohorts. In another hand, the method isn't universally diagnostic, as some heart conditions potentially don't affect ECG amplitudes. Furthermore, real-world use demands prospective trials to test clinical impact. And reliance on PhysioNet data may possibly limit generalizability across global population. These challenges guide further refinements. Our study validated ECG amplitude variability as reliable diagnostic marker, distinguishing normal function, pacemaker patient arrhythmia, and morphological abnormalities. Using PyCaret AutoML as calibrated random forest achieved over 95 accuracy and ALUC over 96 across all classes. Shape analysis ensured interpretability, highlighting skewness and kurtosis as key predictors. Together, this result established a transparent, high-performing foundation for clinically applicable decision support in early cardiovascular disease detection. Looking ahead, we have identified several clear directions for extending and strengthening this research. For the first, we plan to extend analysis to time variability functions. For second, we validate on a large multi-center cohorts. And finally, we will integrate with comprehensive ECG feature sets. Thank you for your attention.
Dear Yuri, thank you very much for your fascinating speech. And dear colleagues, the platform is now ready for your insightful questions and remarks. I would like to clarify something, if you may. So your focus on amplitude variability is quite intriguing. Which specific cardiac conditions are best detected using these statistical descriptors compared to traditional methods?
Our pipeline will be constructed with a few applicable methods, and we use to construct it and further improve. For the current stage, we focused our attention on the amplitude variability between current and previous cardiac peaks. As you can see, this amplitude variability can distinguish different class of morphological, especially morphological states of patients. Potentially, we can work and improve our approach to apply it for variable device and some kind of it. For current stage, we use PhysioNet data set with records in relaxed condition of patients in control environment.
Okay, understood, and quite satisfied with the answer. Dear participants, any other inquiries? If none, that's all for this talk. Dear Yuri, thank you again for your speech, and let's proceed. Our second presentation within this session is on the detection of intestinal thrombosis using a hybrid method based on genetic algorithm and gray wolf optimization. Presenting these work are Любомир Чигирин, Dmitro Ugrin, Yuri Ushchenko, Alexei Ilyuk, and Yuri Masakevich. Dear authors.
Yeah, I'm here. So I'm starting some presentation. You see?
Yes, we can see the presentation. That would be nice if you just started. Okay, the floor is yours.
Thanks. Thanks. Hello, everyone. Today I will present our research how we detection of intestinal thrombosis using and how we use hybrid method based on genetic algorithms, and how we used PCO and gray wolf optimization. Our goals is to improve the detection accuracy of hidden genes associated with intestinal thrombosis, particularly in genomic regions that are traditional, difficult to analyze. So the proposed hybrid algorithm combines the strength of nature in spirit optimization method to have both speed and precision. So some concept of the hybrid approach have four steps. Some main idea is match two evaluation paradigms. This is a gray wolf optimization working with PCO and genetic algorithms. PCO acts as an explored fast scanning large genomic datasets, so close to promised candidate regions. The GI performs refinement approach selection, crossover, mutation, evolve better gen representation. So this combination also exploit a global exploration from approach use PCO and gray wolf optimization and local optimization from GA. This approach can give more accurate results when we used the method alone. Motivation. While our model is primarily biomedical, it was inspired for military genomics. We focused on indefinite genomes related to stress, resolve physical use and critical traits for soldiers' extreme environments. The same computation principle that help detect thrombosis can help reveal genetic marks linked to combine and PTSD prevention. Processing of genomic data before optimization. Also, we must prepare to this processing. This perform combined is filtering, normalization, transformation step, and prepare to scenarios for analytics. Occurrence preprocessing, another that algorithms can detect stable genetic variables linked to thrombosis and physiological adaptations. Next, this is some multi-steps optimization workflow. This optimization consists of four main stage. First stage, preprocessing, clean and normalized data. Second stage is it used scanning phase. We have 15 particles explore. the genomic research next. This is a J refinement, selection, mutation, and refine some result for giving. And the last step is validation under stress. This is a simulation of combined condition tests, the reliability of this model. Next, validation and parameters tuning. We used simulate stress condition to emulate how genetic regulation change under extreme environment, and the algorithm retained the top of 20th best solution when we used selection step, and when we use crossover, this approach. This approach some effective information exchange while mutation step permit convergence. Validation and some performance. The hybrid approach improved both the accuracy and speed of gene detection, compared optimization techniques. These complex regions like detection accuracy increasing by 13%. Their results confirm that combine swarm intelligence environment refinement, and we can see a high effective for biological data analysis. How we improved and detection accuracy. First, it's a medical perspective. For this is some main basis for this approach. And this time, when we can early identification of risk genes associated with thrombosis and stress-related disorders. It can also support step medicine, helping design tailored prevention programs, customizing training for personal and pattern specific strategies. Some stress the hybrid model is not have alignment to medicine. It can help. It can help identify resistant genes potential crop fields by 15 to 22%. In ecology, it improves genomes analytic for species. We can give a shortened clinical trial cycle by 10 to 15%, and optimize gene interaction analytics. To conclude, the hybrid approach, this algorithm provides a powerful the adaptive framework from genomic data analytics, and bridge the gap between global explorer and local optimization when we want to give a better accuracy and detection hiding on stress responsible gens. Thanks, dear colleagues. I ready to question.
Dear Alexei, thank you very much for such a great presentation and your talk. I would like to welcome our participants with their questions, if any. First and foremost, I would like to clarify something. So, given the sensitive nature of your work, how can explainability principles help ensure this technology is applied ethically and responsibly?
Okay, thanks for question. I think it's a difficult goal. My common thing about this, I'm started for basic how and when we choose this approach. We choose a hybrid approach because these methods giving our used many job area with technologies. We can use the machine learning. We can use the simple classic method and algorithm. For example, end colonial algorithm. This is a very good choose methods because we can use in when we training model, we can choose this algorithm when end colony going and leave for road some pheromone. This pheromone we choose in area. It's a very good road to adaptive algorithms.
Understood. Sincerely appreciate your profound answer. Dear colleagues, any other remarks, inquiries, clarifications to Alexei? If none, so that's all the time we have for questions. Let's thank the speaker for his speech and answers. Thank you very much, Alexei.
Thanks.
Okay, next in our timeline, we will hear about a benchmark methodology for urban traffic pattern clustering using SUMO-based expert-verified ground truth. The authors are Vitaly Pavlyshin, Eduard Mardzuk, Adnaner B. Neboysya-Bakanin, and Yuri Krak. Dear Vitaly, the floor is yours.
Okay, thank you. Let me share my screen. Good day. My name is Vitaly Pavlyshin, and the subject of my presentation today is a benchmark methodology for urban traffic clustering using SUMO-based expert-verified ground truth. Excuse me, for some reason I can't switch to the next slide. Okay, now. As urbanization grows and city traffic becomes increasingly intense, transportation has become a major contributor to carbon dioxide emissions. In fact, it accounts for more than 1/3 of all emissions from urban energy consumption. And reducing this impact requires not only better traffic management, but also a deep understanding on how traffic patterns form and evolve within cities. And this research is focused on a critical gap in the process: the lack of reliable methods for evaluating how well different clustering algorithms can identify real traffic patterns. Most existing studies rely on GPS or traffic detection data, which, while is definitely useful, doesn't have a ground truth, meaning there is no objective way to measure how accurate the clustering results really actually are. This makes it extremely difficult to compare algorithms or to select the best one for traffic management applications. To address this issue, the study proposed a new standardized methodology for controlled comparison of clustering algorithm that uses expert-verified reference datasets that simulate realistic urban traffic conditions. This approach enables objective evaluation of clustering quality in a way that closely reflects real-world scenario. Moreover, the research explored how different methods of aggregating transport data affect clustering performance, an insight that has direct implication for designing smarter general traffic management system. And ultimately, this work contributes to our much broader goal of reducing carbon dioxide emission by optimizing the overall traffic flow. What we can find in related works and studies. Research on urban traffic clustering is rapidly expanding due to the urgent need to cut carbon dioxide emission from transport. In the studies, there is a domination of two main approaches of traffic clustering. Those are centroid-based either or means, which is simple but has its own limitations, and density-based, which is HDB scan. It is much more flexible, can detect variable density cluster and noise. Hybrid and graph-based models now track traffic patterns over time and improve forecasting. HDB scan stands for its ability to automatically find cluster numbers and handle real-world traffic complexity. But despite all these advances, research still lack benchmark datasets to test algorithms fairly. This slide shows I'm going to describe overall approach for how we are going to compare clustering algorithms. The full simulation of urban mobility software is going to be used for this research. A map of city of Khmelnytskyi is constructed here with all main traffic lines and lights represented. Using empirical knowledge, several traffic patterns are assembled and are put into Sumo simulation, so the software can run those and output simulation results. Next, we created a model of traffic state representing a way to receive state vectors to be used in clustering algorithm. Based on clustering results, patterns were recognized and datasets were formed. Then various metrics can be calculated for each clustering result, allowing to compare each algorithm and approach performance. It is important to note that traffic models can be created, that we created was targeted to be absolutely compatible with data observable from video surveillance of actual city intersection. And as a result, making a simulation model and real life model fully compatible. Now let's review ExplAI in more details. First, what we need is a prepared environment where the simulation will be run. As I mentioned before, we used my native city of Khmelnytskyi. We recreated it in Sumo. Next, using our expert knowledge, we defined 4 traffic patterns that, to the best of our knowledge, correspond to real traffic conditions in our city. We have typical business day morning scenario with all vehicles moving from sleeping district to business districts. Evening scenario when people are returning from home. Medium intensity all directions traffic, which is typical to weekend days. And traffic movement versus specific city region. This could happen during various holiday days. These patterns were implemented as Sumo scenario. All was done with end goal in mind, that the same representation model as those we used for simulation can be recreated as well from observation and from optical recognition. Next, we united all the defined patterns on the previous step into one big Sumo simulation. Our identified patterns were mixed in the simulation, and slight variance for both traffic intensity and duration was introduced. Overall, the simulation time was 11 hours. On the city map, we defined a key intersection using which we are going to describe and store traffic states. There are 10 intersections total, which host 70 traffic lines, and those will be used later for traffic state model. Next, we need to prepare vectors that will be passed later for clustering algorithm. For this flyent and continuous traffic is broken into time windows of fixed duration, 30 minutes each. Windows are taken every 10 minutes with 20 minutes observation lap, with 20 minutes overlap between two consecutive windows. Within each window, every 10 seconds, we collect numbers of vehicles on each defined line of all intersections we defined earlier. From this data, we form two vectors. Concatenated values, where we simply concatenate all the numbers for all time steps, and average data, where we store average value from all values of the time window per each line. We end up with 12,000 with vector of 12,000 dimension vector for concatenated values and 70 dimension vector for averaged values. For vectors created in previous steps, we form dataset for clustering and apply ground truth labels. Each vector corresponds to its specific time window, and knowing window of sets, we can apply ground truth label to each vector accordingly. Those are based on the 11-hour scenario that we created that I mentioned earlier, with various traffic patterns following one another. Next, we defined 6 clustering algorithms to apply and to compare performance. Those are affinity propagation, mean shift, Bayesian GMM, agglomerative clustering, HDB scan, K-means. For clustering, we used concatenated vectors, concatenated value vectors, and aggregated value vectors, and produced 14 different clustering results, performance of each to be measured later. This slide shows internal clustering quality metrics that we collected and obtained, from our obtained results. Those do not depend on ground truth label and mostly measure clustering density and separation. Here we show external clustering quality metrics. These are based on ground truth label. They evaluate accuracy of recognition. On this slide, we visualized the returned results. We did not show all the metrics here on this chart, but only one from internal and one from external, which are silhouette score on x-axis and adjusted rand index on y-axis. Both metrics are interpreted in a way that higher value means better results. For this chart, this means that most accurate results are situated at top right corner. The more closer to top right corner, the better result is considered to be. Also, we here used circles for average data and triangles for corresponding concatenated data vectors. Results of same clustering algorithms are connected with lines. What we can instantly see from this chart is, in general, average data always performs better than corresponding concatenated data. RGB scan on average data produces the most reliable results, followed by K-means with 5 centroids. Performance of other algorithm you can see visible on this chart as well. Conclusions. As was mentioned here, we confirmed that HDB scan is superior comparing to other algorithm, and next is followed by K-means. Also, but in a way, all algorithms showed better performance on average traffic representation than on concatenated results. All results and more detailed comparison can be found in the article corresponding to this presentation. Thank you for your attention.
Thank you, and I greatly appreciate Vitaly's fascinating speech. I would like to welcome our fellow colleagues with their inquiries, if any. Me personally would like to clarify one thing. So your results favor aggregated data, but what key temporal information is lost in this process, and when might a more detailed view still be necessary?
That's a very good question, and it's something that brought us again, that created some thoughts on our side as well. Indeed, with aggregated value, we lost dynamic. Like currently, for concatenated values, we have pretty much state described at every time at every position during simulation. But for aggregated, it's like there is no dynamic. The dynamic is lost. So if some pattern is characterized by some, let's say, increasing value of traffic during initial time and then graduate reducial, this will be lost. And that's very good observation. What can we do here? We probably need to think about different representation of like creating different model that has not only full values, which are too large, but somehow differently aggregated. This is something to think about. With this, how I personally explain it, with my human mind, if I can think, like if I'm thinking of my city of Khmelnytskyi and I'm asked to describe the behavior of traffic, let's say in the morning, my mind instantly shows me an image of line and how large the waiting queue is for a specific intersection. And my mind pretty much generates always average number of vehicles that normally are standing there. Like I never think, okay, at 9 a.m. it's like 3 vehicles and on 10 p.m. it's like 5 vehicles. It's not how I think as a human. So as a result, maybe this is even okay. And maybe this dynamic is not really needed. But still, it's a good question. Still, it needs to be proven. Like at this point of time, I have no neither good arguments to support this point of view or to break this point of view. So I just provided you both to judge.
Yeah, clearly understood, and I'm very glad with your profound and comprehensive reply to this comprehensive question. Okay, dear colleagues, any other questions? If none, then that's all the time we have for questions within this talk. Let's thank the speaker for his speech and answers again. Thank you, Vitaly. And to conclude this session, we will move on. And we have knowledge engineering information technology for cultural educational scenarios based on RAG, or which is also called RAG. This work is by Kristina Lepyanina-Goncharenko and her team Nazar Melnik, Miroslav Komar, Pavlo Bykovy, and Kristina Yurkiv. Please, dear authors, the platform is yours.
Thank you very much, Pavlo. So Pavlo already presented our topic, and so RAG is retrieval augmented generation. So I would like to say that this work is made within the project of Creative Europe program, which is aimed to build a trustworthy AI storytelling for museums and educational institutions. So task what we are doing now. So we deal with museums and cultural institutions to collect data and make their exponents alive. So their exponents should answer questions what visitors can give to them. So what is the problem with museums? Museums now are afraid of losing of visitors, and they are trying to attract visitors by different way. Yeah. So one of the point is to make let's say personal approaches, to make multi-language translation, multilingual support, to make interactive learning. Digital technology help with it. Yeah. Sorry, I cannot switch slides. Okay. So the aim of our work is the development RAG knowledge generating technology, which enable us where we build a licensing component and reproducible knowledge corpus, ensure semantic search, re-ranking of fragments, generate grounded responses, provide safety policies in case museums are afraid that different people, so they were afraid if children ask questions and adult persons ask questions, so here is different type of questions and it should be different answer. Yeah? Even when question is the same, answer should be different, like for children or for children or for adults. So, good. So here is provided technology. So it has different steps. Basic steps are in collection and parsing of input data, what will be used for training model. Collection, verification, cleaning, corpus versioning, segmentation, knowledge verification, preparation and indexing of data. Other steps are work after this preparation. Yeah, system will provide it will be possible to make a configuration of the system, provide safety and moderation policies, provide client flow configuration, and finally be able to make analysis to get knowledge retrieval and testing of results and evaluate of the answer of the system. So here is structure of the system divided by two user stories. So we have two type of people here in the system. We have administrators. So administrators are providing input of the data and provide the system prompt. And basing on this, the model of each exponent is generated, and then this model is used when user log into the system, select exhibit what he would like to talk. So in the future, project requires that people not type but do talking. Yeah, so it will be implemented system for conversion from text to voice. But for now, for this stage, we have only text version to test and debug the system. Yeah, so we have different pre-trained, in this case, models. So, for example, exponents here we have Leslie Krinkel, Leonardo da Vinci, William Shakespeare, and depending on what type of user, if it is adult or child, and what was the prompt provided by administrator, the user will have different answers. So here is some screens from administrator side that we can upload here. Some text, provide exhibit name, provide for what type of audience it is. So this is prompt. So this is next part of the administrator page, where administrator provide prompt what should be used to give more correct result, to adjust the result provided by the model. And this is a user interface, so where what users can see when they talk with
in our case with Jan Tarnowski. So they give him a question and receive answer, and we tried to simulate and get some results. And next step is to verify and to adjust how provided model is answering the questions, if it is correct, if it's not correct. So for now, this is like first stage of our investigation. Yeah, so we just do some accuracy or relevance and check for ethical tone. Yeah, so we provide for paper for presentation of results 8 questions. So some of them has different verification goal, and so let's say first question, if it is in first person narrative, it should has inside some biographical facts and core corpus. Other question also has their specialty. For some question, model should answer that is not their field, and so on. Yeah, so we check it for now manually, and so when we talk with the model, if we provide question in Ukrainian, we get answer in Ukrainian. If we provide question in English or other language, we get answer in this language. Good. So let's say for each question we obtain some answers, yeah, and we check, let's say, content faithfulness, if basic words are present, if it is, let's say, correct, and so on. Yeah. So we give model different question and receive answer. You can get acquainted with it in our paper. Yeah, more detailed. Here is some statistics. What we obtained from our 8 questions and answers, and good to say that preparation of prompt is very sensitive part of this work. Therefore, there is a lot of adjustments and the basic keywords of the system. So during the implementation, it will be used to adjust answering more correctly and more reliable to the museum or what is required. Yeah. So let's say this is a template how some prompt should look like. Yeah. And in general, there are different fields like audience, adult, kids. If model of the answer should be simple or strict, if identity should be provided, depth of the persona, knowledge area, to limit the person. Let's say museums workers, let's say, were afraid, like, because when you talk about somebody from the past, it's like you are speaking with a ghost. Yeah. So they wanted to adjust precisely that, let's say, people from the past, they will not answer the questions about current situation in Ukraine, for example. Yes, they don't know who is Zelensky and so on. Yeah. So when you ask such persons such questions, they should say it politely that this is not their area and so on. Other characteristics like response length, knowledge source, the safety level, and so on. Yeah. Thank you for your attention, and it was nice to me to join your conference. And if you have any questions, please.
Dear Pavlo, I'm grateful to you for your wonderful talk. Let's hear our colleagues with their questions or possible remarks. Yeah, please, Alexei.
Thanks. I saw a very good diagram of data set and the models. Are you considering a multi-language HCM system using with technology Azure in the future? How do you think?
So let's say now we didn't move to the separate, let's say, cloud technology. So this is our next step, okay, to make voice and so on. Yeah, so it will be next part of the work to do on this point. Yeah, so we didn't decide what technology we should use for the next step.
Very good job. Very good job. I see some great model. Thanks.
Okay, thank you very much.
Thank you, Alexei. Thank you, Pavlo. One more question from me. Your token exhibits are a great concept. How important do you think is the honest uncertainty policy for building trust with users, especially with children?
Yeah, so I mentioned that let's say museums, they are very afraid of receiving some hallucinations from the model, yes, and receiving not correct answer. Therefore, we should be strict with the data what we give and the possible questions and answers. Yeah, but so let's say we are in the testing stage, and we, let's say, prepare for now our system, which will run, let's say, auto test for the model. It will give different questions. For example, even when you give the same question, you will receive not similar answer, but not 100% the same answer. Yeah. So let's say we are in the stage where when we investigating how to avoid and how to reduce these false answers and so on.
Great. Thank you very much. I'm fully satisfied with the answer. Dear colleagues, any other inquiries? Okay, so that's all the time we have for the questions within this talk. I shall thank the speaker once again for his participation. Thank you very much, Pavlo.
Thank you.
Excellent. That brings us to the end of our third session. We are scheduled for another 15 minutes break. We will begin our final presentation session at 12:45 p.m. So see ya and hear in 15 minutes. Dear participants, welcome back for our fourth and final session of the day titled Trustworthy AI. We have 4 more high-quality contributions to hear about. We begin this time with vision transformers transfer learning for smoking detection in public places with transparent AI decisions. The authors are Alexander Mazurets, Marina Molchanova, Olga Zavutska, Igor Kok, Vitaly Lavashenko, and Abdel Badai and Salem. Dear authors, who is going to present this work?
Yes, I'm here. Just a second.
Great.
So can you see my screen? Is everything okay?
Just a second. It is being shared. Yeah, now we can see everything. So the word for you.
Thank you. So good afternoon, dear colleagues. My name is Olga Zavutska, and I'm pleased to present you the topic Vision Transform and Transfer Learning for smoking detection in public spaces with transparent AI decisions. As we know, tobacco smoking causes numerous diseases, and of course, it's significantly lowering the life quality and increasing healthcare costs. Despite legal bans on smoking in public places, enforcement is still relies on limited human resources. Deep learning-based computer vision offers new possibilities for automated surveillance systems that can detect smoking in real time with high accuracy, helping to prevent passive smoking and improve public safety, especially in crowded areas. This topic aligns with the UN Sustainable Development Goals. These are goal number 3, good health and well-being, and goal number 11, sustainable cities and communities. And main goals and contributions of this research. Goal is improving smoking detection accuracy in images using transfer learning with vision transformers and transparent AI decisions. Contribution is developing a deep learning-based method with partial parameter freezing and data augmentation, enhancing adaptability to limited datasets, and integrating heat map visualization to ensure interpretability and trust in neural network decisions. Although deep learning-based smoking detection has advanced, the current model struggles with small datasets and varying environments. Many vision models require extensive label data, limited real-world applicability. This study explores how transfer learning with implementation of vision transformers can enhance smoking detection under data-scarce conditions. The key research question is whether such adaptation can boost accuracy while ensuring transparency and correct attention localization in images. So here you can see scheme and steps of the smoking detection in public spaces method. The input data are images for analysis and trained neural network model. In step 1, the image is preprocessed according to the requirements of the VIT model. After that, the image is automatically partitioned into non-overlapping patches of 16 by 16 pixels, each of which is prepared for further vector encoding. The result of this stage is a representation vector for the entire image, a classification token which contains generalized information about the image. And the resulting vector representation obtained in step 3 is passed to the final linear layer, which was trained for binary classification. The output value is interpreted as a logit, which characterizes the probability of the presence of smoking in public areas. In the study, the threshold was taken as 0.5. If less than 0.5, the class is non-smoker, and otherwise it equals to smoker. In order to interpret the model solution, the step 4 is performed, the grad-CAM method is applied, and based on the calculated gradients, a heat map is formed and overlapped on the image. It shows which areas of the image were decisive for the decision, increasing transparency and confidence in the model. The output data are the class, smoker or non-smoker, and numerical score of the presence of smoking in the range from 0 to 1, and the heat map. Here you can see a neural network model. As I said, at the classification stage, image is preprocessed and divided into patches. Each patch is linearly projected into a feature vector combined with a CLS token, forming input token for the vision transformer. Each block includes a multi-head self-attention and MLP layers with normalization, enabling the model to capture long-range special dependencies. The updated CLS token is passed to a linear classification head with segment activation function and output in smoker or non-smoker class. To enhance efficiency, only the final layer is trained, partial parameter freezing, while pre-trained weights with stochastic class averaging Gaussian was used. This approach reduces computational cost, ensures stability on small data sets, and maintains high classification quality under varying conditions. A couple of words about the dataset. The dataset was obtained from the Kaggle platform, and this dataset represents a balanced sample of visual data consistent of two semantic categories, smokers and non-smokers. And main feature about this dataset is the presence of a high degree of interclass similarity. Images in both classes was selected in such way as to contain poses and gestures that are visually close to smoking X in order to complicate the classification task. So this kind of selection strategy increases the discriminatory power of the model and stimulates it to learn deeper contextual features. To validate the proposed method, we created an application using Google Colab, Python, TensorFlow, Keras, GradCAM, Matplotlib, and OpenCV. And here you can see some examples of image analysis for detecting smoking in public spaces. The first photo was given from the dataset, and the second photo it's from our author ear, and you can see here that he is obviously smoking, and the model shows this. And some results. Training results are represented as a confusion matrix, ROC curve, and a classification report. High precision and recall value demonstrate the model's strong generalization and lack of class bias, and is crucial for behavioral analytic tasks. As you can see, the loss curve confers stable learning without overfitting, validating the hypothesis that transfer learning with vision transformer model can achieve high detection accuracy even on limited datasets. And here you can see heat maps. Some heat maps. The heat map results show that the model demonstrates high accuracy and semantically meaningful attention. Active regions focus on the mouse, face, and cigarette, confirming the model's ability to learn relevant visual patterns of smoking behavior. So this proves that the network is not a black box, as its decisions can be interpreted through visual attention, increasing trust and transparency in AI-based detection. The proposed vision transformer-based model with image transformations and weight freezing achieved high accuracy of 0.89, suppressing other models, and these balance, precision, recall, and F1 score confirm improved classification and reduced false positives and negatives. So these results demonstrate that width-based approach outperforms both CNN and object detection models, proving its effectiveness for automated smoking decision in public spaces. And some conclusions. A transfer learning method for smoking detection in public spaces was proposed, ensuring transparent AI decisions and improved detection accuracy. The accuracy increased compared to other models, and compared to YOLO version 5, small heat map visualizations confirmed correct attention zones, enhancing trust and interpretability of AI decisions. The approach uses partial parameter freezing, which prevents overfitting and reduces computational costs. Stochastic weights averaging improved training stability and validation performance, and comprehensive preprocessing ensured robustness to varying lighting and shooting conditions. That's all. Thank you for your attention.
Dear Olga, thank you very much for such a splendid talk. Now the ground is open for questions. And one will be from me. Dear Olga, how do you see the GradCam heat maps helping to build public trust and support the adoption of smoking detection technology?
Thank you for your question. So I'll just turn to this slide. So as you can see at these heat maps, we can kind of translate the decision of our model, and we can make sure that our model and its decisions are right, because the main zones of attention are concentrated in the right places. Or what do I mean when I say right places? It's a cigarette, it's a hand, like wrist, and parts of our faces. So we can see that GradCIM method is not just like highlighting any random pieces. It concentrates its attention on the right places. So actually, with this, with applying of this technology, we can like make sure that our model is stable and its decisions were made correctly. So applying this kind of explainable AI, I guess it's really useful for this kind of technologies, because it's really important to concentrate this attention on the right zones and don't predict any wrong answers, because it can be used in a wrong way and make a little mess.
Okay, everything is clear to me. Thank you very much.
Thank you.
Dear fellows, any other inquiries, remarks? If none, so that will be all time we have for the questions. Let's thank the speaker again. Our second talk is an approach to matching satellite and UAV images for visual place recognition using color normalization and YOLO. Presenting this work are Volodymyr Wozniak, Yuri Ushchenko, and Orkan Mamburbayev. Dear Volodymyr, I suppose the presenter will be you, so the platform is up to you.
Yeah, hello everyone. Can you see my screen now with the presentation?
Yeah, the screen is fine.
Yeah, okay, so good. So hello everyone one more time. Today I want to show you a presentation for an article for with the topic of an approach to matching satellite and UAV images for visual place recognition using color normalization and YOLO. My name is Volodymyr Wozniak and I'm a PhD student at Khmelnytskyi National University. So let's start. Here's fast content of this presentation, but let's move on. Let's start with the motivation and state of the art. So the accurate determination of UAV's location under challenging conditions plays a decisive role in numerous applications, from rescue operations to mapping and industrial inspections. In areas with strong radio interference or compromised GPS signals, methods based on the analysis of images acquired from onboard UAV cameras and corresponding satellite imagery of the terrain can assume a critical role. And some words about state of the art. CNN-based visual place recognition methods, also computational efficient, they require training on large specialized data sets, and transform-based methods provide high-quality vector features, usable without additional fine-tuning, but they remain really slow compared to CNN models, complicating deployment them on UAV platforms. Using YOLO, a CNN-based model renowned for real-time efficiency and high accuracy, has not yet gained really high popularity in VPR. That's why we choose this model for our research. So some words about the objective. The study aims to enhance the accuracy of CNN-based methods for UAV global location determination in urban environments using models capable of extremely fast real-time image processing. The contribution of this research includes obtaining vector representations of images from convolution layers of a fine-tuned YOLO 11 model trained on a dataset of segmented buildings, and determining the global location of UAVs using average cumulative distribution functions of images, which enables more precise matching between UAV imagery and satellite images. So here you can see a processing model. It's a general data processing scheme for determining UAV location coordinates. So for input, we have like satellite images and UAV images. Then we are trying to determine the global location, then determine the precise coordinates, and have an output UAV coordinates, final UAV coordinates. But this work is targeted on this step, determining the global location. And here you can see a processing scheme for UAV global localization using the proposed image preprocessing method and a YOLO 11 model fine-tuned on a dataset of segmented buildings. And so here we can see that we have like a database of satellite images that have been already processed through the YOLO 11 model, and we have some vector representation for these images already pre-calculated, and we have like a database of this vector representation. And then when our UAV flies, we can have like an image in real time, pass it through our image preprocessing method, pass through a YOLO 11 model, get an image representation vector for the particular UAV image in real time, get a UAV image representation vector, and make a similarity search through the database of satellite image to determine the global location of our UAV in real time. So here we can see a YOLO fine-tuning results, an example of building segmentation on an image from the test dataset using for fine-tuning YOLO 11. And here is an example of building segmentation on an image from the VPAR dataset, which was used for our visual place recognition pipeline. And here some final metrics for fine-tuned YOLO 11 model on the segmented building dataset, and we can see that it works pretty much the same for every random splitting, which is good for us. And some YOLO fine-tuning discussion in the context of building segmentation. An F1 score of 0.72 for the test dataset can be considered a positive outcome, especially given zero time speed advantages inherent to the YOLO model family. The trained model reliably identifies buildings crucial for generating the vector representation used for UAV global localization, and the standard deviation of each metric across both training and testing dataset is below 0.5%, indicating consistent model performance. Let us move to image preprocessing method results. Here we can see some visual results of the proposed average cumulative distribution function method applied to UAV images, aligning the statistical distributions with those of satellite images. So here we can see original satellite images, original UAV images, and transformed UAV images. And as we can see, we have like for transformed UAV images, they are pretty similar with colors to our original satellite images. And here's a table of results for image preprocessing method. Here we can see the recall one metric results with localization radius of 3 across different terrain types, and our targeted terrain type is urban environment. And some discussion about these results. These results indicate that CNN-based methods Cosplace and YOLO perform better with the proposed preprocessing method, confirming its capability to enhance UAV global localization accuracy. Also, Cosplace performs better in fields, forests, and water terrains. The proposed YOLO-based method achieves superior results in urban environments, our targeted terrain, due to YOLO 11's fine-tuning on segmented building data. And considering the inherent complexity of UAV global localization, where many approaches struggle to maintain high accuracy at top ranks, I recall one value of 0.195 or 19.5% with localization radius of 3 for urban terrain is a promising outcome. And some final conclusions. For vision-based UAV localization, models should be interpretable and auditable. Fairness entails monitoring performance across neighborhoods, architectural style, season, and sensor domains to avoid systematic disparities. Reproducibility benefits from fixed seeds, documented splits, and transparent releases of code or configs, plus model cards that state limits and intended use. The primary objective of this research was successfully achieved, enhancing CNN-based methods accuracy for UAV global localization in urban environments using models capable of real-time image processing. YOLO 11 fine-tuned on segmentability data was employed as the model, and the obtained quantitative results include an F1 score of 0.72 for the fine-tuned YOLO 11 model, considered good for billion segmentation task, and a recall one value of 0.19 with a localization radius of 3 for UAV global localization in urban areas, surpassing cosplays by 0.05. So thank you for the attention.
Thank you very much, dear Volodymyr. I deeply appreciate such a wonderful speech. And I would like to welcome our dear participants with their questions or remarks, if any. For Zahar, any questions?
Thank you, Volodymyr, for presentation. Could you please clarify how would weather conditions influence your pipeline?
Yes, thanks for the question. So now we have some limitation for weather conditions. We must have like pretty good images for both satellite and UAV. And it's like a high limitation for us, but we are currently working on some augmentation that allowing us to work with different weather conditions. For example, we want to add snow weather or like fog weather, night time for UAV images. And we want to also add this augmentation for our data sets that was used for fine-tuning YOLO 11 model. And like we have some problems there because we want to use diffusion models for these augmentations, and it is important to us to have the masks for the building keep constant because we do not want to change like the position of different elements of on the image, but we want to like have the original image, but only with some weather augmentation, like adding snow, adding fog, adding nighttime, etc. And then we want to fine-tune YOLO model on data with weather augmentation, and then we can like say that our visual place recognition pipeline can work in different weather conditions.
Thank you for your answer.
Thank you, Zahar and Volodymyr. And one more question will be from me. How could you incorporate explainability to show a user why the system made a particular image match, which is vital for trust in navigation?
Yeah, for now we like can show different buildings. For example, we can show like which building was found on the satellite images, which building was found on the UAV images, and like give some insights about the match on a particular step in real time, like highlighting these buildings on these images.
Okay, great. And thank you very much. Dear colleagues, any other questions? If none, then that's all for this presentation. Let's thank the speaker once again.
Yes, and
All right. Next up is verifiable by construction, evidence-anchored LLMs for explainable fake news detection. This research is by Andrei Shupta, Pavlo Radyuk, Miroslav Klasai, and Piotr Gadjin. Whoops. The presenter of this work was supposed to be Andrei Shupta, one of my co-authors. Unfortunately, due to the electricity shortages, he is unable right now. So I will personally present this work as a co-author. Just a second. Sharing screen. Let's check the presentation. Okay, everything is clear and is visible. So, dear colleagues, on behalf of my co-authors, I'm honored to present our research verifiable by construction, evidence-anchored LLMs for explainable fake news detection. This work is a collaborative effort between Khmelnytskyi National University, Zilina University, and the Silesian University of Technology. Today, I will start with an introduction to the problem, then detail our proposed framework. After covering the experimental setup, I'll walk you through our results and analysis and finish with our conclusion. First, we begin with the core problem, an infodemic fueled by generative AI, which can mass-produce plausible fake news. This poses severe threats to our society and creates an urgent need for robust detection systems. However, the most accurate AI models are often untransparent black boxes. They provide a verdict without any justification, and this lack of explainability is a critical barrier to trust and real-world adoption. This leads this leads us to our core belief. Interpretability should not be a post hoc feature. Instead, it must be an a priori design constraint woven into the entire modeling lifecycle from the very beginning. To achieve this, we introduce the XFND framework, so-called a human-centered pipeline for building trustworthy detectors. Our first key contribution is human-guided validation, or HGIVR, a visual analytics framework that allows experts to shape the feature space before training. Our second contribution is evidence-anchored explanations, or EAECS. This is a model that generates faithful natural language explanations that are grounded in verifiable textual evidence from the source document. Finally, we provide a complete implementation of our framework. This ensures our findings on public benchmarks like Liar and FakeNewsNet are fully reproducible and available to the research community. Our framework uses a three-stage pipeline. It begins with feature engineering, where we extract features like sentiment and crucially link each one to its exact textual evidence. In the second stage, experts perform the so-called human-guided validation. Using interactive visualizations, they iteratively refine the feature set to ensure its quality and coherence before any model is trained. In the final stage, a model predicts the class, and our explanation model synthesizes a justification. This explanation is strictly based on the stored evidence for the most important features. The key idea is that the entire pipeline is designed to be verifiable. We can trace the final explanation all the way back to the raw text in the original article. Now, let's look closer at the HGIVR protocol. Its primary goal is to iteratively improve the feature space with direct expert guidance, ensuring the model learns from meaningful signals. The process involves experts visualizing the data, checking separability metrics, and refining the feature set until the class clusters are clear and semantically meaningful. The main benefit of this approach is that it shifts explainability from a post hoc analysis into a prospective design choice, building trust from the ground up. Next is the EA-ECS protocol for generating explanations. Its goal is to create justification that are faithful to the model's logic by design. The process identifies the key predictive features, that retrieves the pre-recorded textual evidence, and uses an LLM simply to narrate these facts without adding outside information. This strictly constrained approach prevents the so-called LLM hallucination. It ensures every part of the explanation is directly and verifiably tied into the model's reasoning and the source text. For our experiments, we used the liar and fake news net datasets. Our classifier was a calibrated support vector machine, and we focused on evaluating feature space quality, model performance, and the trustworthiness of explanations. Our results show that HD IVR process measurably improves class separability. The silhouette score increased significantly for all datasets after expert refinement, confirming the value of this pre-training step. This improvement is also clear visually. On the left, the initial liar dataset shows heavily overlapping classes. After HDIVR on the right, the classes are much more distinct and evidently even well-structured. Similarly, for the binary tasks in fake news net, we see that the refined feature spaces for both PolitiFact and GossipCop show clear geometric separation between classes. In terms of performance, XFND achieves strong and well-calibrated results on the liar dataset, outperforming baselines in the 6-way task and showing high accuracy and F1 score in the binary task. Our model also proves to be highly reliable. The calibration curve to the left shows its predicted probabilities are accurate, and the confusion matrix reveals that errors occur logically between adjacent categories. On fake news net, our content-only XFND model is competitive with, and in some cases outperforms, fusion models that use additional social network data, demonstrating the power of a well-crafted feature space. The classifier shows excellent discriminative power of PolitiFact. Both the ROC and precision recall curves indicate a strong, robust ability to distinguish between real and fake news. This strong performance is maintained on the GossipCop dataset as well. This reinforces our model's effectiveness across different news domains and content types. Finally, our explanations are provably faithful and audible. Removing the evidence we cite causes a significant drop in model confidence, and the high overlap rate shows our explanations are grounded in the source text. In conclusion, we introduced the XFND framework. Our work shifts interpretability from a post hoc analysis to a core design principle. We have shown that the proposed HGIVR demonstrably improves feature space quality, leading to more robust and reliable models. Furthermore, EA-ECS generates explanations that are faithful to the model's reasoning and anchored in verifiable textual evidence. Our approach achieves competitive accuracy and strong calibration, proving that transparency and performance can and should coexist. Finally, the key takeaway is this: the XFND paradigm that we propose in our work offers a blueprint for creating trustworthy and explainable AI systems that function not as an untransparent or even opaque oracles, but as collaborative partners in the fight against misinformation. Thank you for your time, and I'm very pleased to answer any of your questions. So, dear colleagues, Alexei.
Thanks. This is a great job. Very great job. I have one question. How is the silhouette score computed in a multi-class multi-class settings as an average across all classes with weighting for only fake, and only real labs?
Thank you very much for your question. We performed performed calculations and calculated silhouette score across all classes without any specific preprocessing with classes.
Thanks. Very interesting approach to this task. Thanks.
Dear colleagues, any other questions? If none, so then let's proceed to our further presentation. So for our final presentation of this workshop, we have the hierarchical neural network model for identifying similar objects in drone images. The authors are Dmytro Borovik, Alexander Barmak, Pavel Komada, and Sergei Babichev. Dear Dmytro, please welcome to your speech.
And good day, everyone. Let me share my screen. Sorry, just a second. Yeah, do you see my screen?
Yes, your presentation is now in full screen mode, so you can proceed.
Yeah, good day, everyone. Today I would like to present our research titled Hierarchical Neural Network Model for Identifying Similar Objects in Drone Images. This work focuses on improving the recognition and grouping of visually similar objects captured by unnamed aerial vehicles. The relevance of these topics has increased significantly due to rapid growth in drone deployments. Modern UAVs collect large amount of higher resolution visual data in real time. Manual analysis of such data is slow, error prone, especially in time critical environments. Hierarchical neural network architecture offer advantages for similarity-based recognition because they analyze visual features progressively from low-level textures to high-level semantic patterns, enabling accurate grouping even under occlusions, variable angles, noise, and light changes. The subject of our work is hierarchical neural network models applied to similar object identification. The object of investigation is with visually similar entities captured in drone imagery under complex conditions, and the purpose is to develop and evaluate a hierarchical approach that improves automated interpretation, increases efficiency, and supports decision making in different environments. To achieve this purpose, we analyzed advanced deep learning architectures such as YOLO, faster RCNN, collected and annotated aerial data sets, trained models to detect civil and military assets, including vehicles, ships, aircraft, and so on. We evaluated performance using accuracy, precision, recall metrics. and checked if everything works in different conditions with different environmental changes like light availability. We applied several research methods, including literature review to explore existing approaches, data collection and annotation to create training sets, and model selection combined with transfer learning to enhance performance. Reprocessing techniques like normalization, augmentation, and augmentation improved our generalization, while experimental evaluation and comparative analysis reveal strengths and limitations of different architectures. Yeah. Proposed approach. The essence of the proposed approach to improve efficiency of object classification in UAV's imagery, it lies in constructing a multi-level structure that classifies objects step by step, gradually refining their classification into specific classes. At each level, a classification is carried out within a limited number of classes, which makes it possible to extract feature characteristics of specific objects more accurately in the case with usage multi-class classification model. A schematic representation of the proposed approach is shown on a slide. This approach is scalable, flexible, and allows new classification level to be applied easily without a need to retain the entire system. Also, in our work, we described a set theoretical model which can describe how everything should be work on the theoretical side. Feature extraction, feature vector selection. At the core of this method is the feature vector extraction strategy, where outputs from different neural models are concatenated. Low-level and high-level representations are combined, providing richer semantic information for the final classifier. Also, the key feature of the proposed approach is that 2 deep learning models are used at each level instead of 1. The first model is responsible for extracting object features and constructing their vector representation based on set and principle, and the second model, in turn, is used directly for classifying the detected objects based on the result of the first model. To demonstrate the proposed approach, the following example is provided. Drawing the empirical observations, we created a 3-level target classification sequence for UAV imagery suggested, which can be seen on this slide. This ensures different shapes, textures, geometry preserved, and so on. A withdrawn dataset was used for training the models used in the feature extraction at different classification levels, and the overall dataset was divided into subsets corresponding to subclasses associated with a specific level of classification. On this slide, you can see experimental results. For example, on first level, system classifies general human presence. On the second level, it focuses on the trucks, as you can see from a slide, and at deeper levels, it determinates between various vehicles like vans, buses, and so on. And with purple, you can see vehicles which were not included into the structure of our approach. So all the other vehicles is combined into one group, and then with adding new levels, we can split them more directly. On this slide, you can see validation result, which with its calculated metrics. Table 1 represents result for withdrawn dataset, and also we validated our approach on a dataset which wasn't used for training. Table 2 represents our result for COPO dataset. Also, we validated our approach in military field. For military environment, the system achieved high precision and recognition vehicles and equipment relevant to battlefield monitoring. It remained robust even with challenging imagery, background noise, and conflict. On this slide, you can see ROC curves, and comparative results in table 4 shows that hierarchical sequential approach overperforms some existing solutions, especially in scenarios with a large number of classes. It achieved superior recall and F1 score, which indicates fewer misdetections and better classification reliability. And in conclusion, this work presents a multi-level system for real-time classification of similar objects, which can be used for different areas. As I provided an example in military, for example, or for civil vehicle classification, combines ALV11 and faster RCNN for detection and feature extraction, and FT transformer for accurate classification. The system achieved more than 94% in precision recall and F1 score while maintaining a real-time processing speed. So, thank you for your attention. I'm open to your questions.
Dear Dmitro, thank you very much for your fascinating talk. Any questions? Yeah, Alexei, please.
Thanks, a very interesting job. I have one question for me interesting. Does the height from which the photo was taken, does it matter? This is the first. If so, is yeah. Have you some database which which information of this database dimensions of objects are optimized? Thanks.
Thank you for the question. Everything depends not on a height of image, but on resolution. As higher image is taken, the better resolution it has to be, because when model works, it tries to find a specific patterns which are very common in a specific vehicle type, if we're talking about provided example. So if image is taken from a low height, then resolution can be not very good. But in general, all shapes and patterns are represented anyway. But if the same resolution will be applied for image which is taken from 3 kilometers, 5 kilometers, then in a result, our vehicles will be just too small to identify something.
Okay, thanks. Last questions. What do you think about learning patterns, update patterns? How instrument use in future maybe?
Yeah, if we're talking about fine-tuning of models, so each model which is used on a specific level is trained on a specific created data set which contains only classes which is applied for this specific level. So on the first level, as we described, we split our data set into people and vehicles and train our model only to make this binary classification, people and vehicles. On the second, we split it further. We take the other vehicles and split it further to trucks, buses, and other vehicles, for example. Then on a third, we again take other vehicles and explode it further, and so on, so on, so on. That's the main idea of this sequential hierarchical architecture, is that the most similar objects we can combine into one class, and then on the next level of classification, split this specific class into smaller classes. And our length between classes, if we're talking about POC analysis or so on, will be more different. For example, if we're talking about buses and trucks, then comparing vehicle to a human. So we'll have different lens, and by this lens we can select the next classes for training.
Thanks. Very interesting job.
Dear Dmitry, dear Alexei, thank you very much for your participations. And colleagues, any other interesting inquiries, maybe? If none, then thank you again. And that's all for this talk. We shall thank the speaker again. So this concludes the presentation portion of our workshop. Let's take one last 25-minute break before we reconvene for the awards and closing remarks at 2 p.m. So wish you a fruitful coffee break, maybe lunch. See you and hear you in approximately 25 minutes. All right, let's proceed. Dear participants, welcome back for the final time. On behalf of the entire organizing committee, I want to extend a sincere thank you to every one of our speakers. Your research has provided a wealth of knowledge and sparked important conversations that will undoubtedly continue long after we leave today. So, as we conclude ExplAI 2025, it's time to recognize outstanding contributions to reflect on our day. The program committee had the difficult task of selecting a best paper from the many high-quality submissions. However, we had a final conclusion. Just let me admit everyone and check whether it's visible. Okay, it's visible. So the award goes to, Yuri Khmelnytskyi and his work titled AutoML, PyCaret, and Sharp Explainable AI for ECG signal classification based on amplitude variability. This work was authored by Dmytro Timoshuk, Irina Didic, Andrei Sverstyuk, Lyubomir Moisey, and Yuri Khmelnytskyi. We decided to give the award specifically to them due to their the most outstanding contribution. Congrats to the authors for the best paper. The program committee has also decided on 2 best presentation awards, and the award goes to 2 presenters. So the first one is Vitaly Alexeiko for his outstanding work, Explainable Artificial Intelligence Foundations for Web-Based Sea Ice Extent Forecasting System, co-authored with Tatiana Gorushenko, Olga Pavlova, Oleg Voichur, Valeria Shvaiko, and Artem Voyarchuk. Great congrats to Vitaly. And the second award goes to Bogdan Romanov for his and his co-workers' work and approach to identifying functional and non-functional requirements in IT project management using deep learning models, authored with Ruslan Bahri, Tatiana Skripnik, Elena Zaitseva, Huda El-Bouhoussi, and Volodymyr Litvinenko. Many congrats to our presenters and to our participants. Wish excellent future work and outstanding results in your further work. Congratulations on this excellent achievement. I also want to thank you, our audience, for your thoughtful questions and active participation. A workshop is only as strong as its community, and you have made this a vibrant and engaging event. Please, I should make a note once again that the workshop proceedings will be submitted to CEUR soon, and authors of high-quality papers will be invited to submit extended versions of the Sustainability Journal. This is a fantastic opportunity to further develop the work you've shared today. Further notes will be emailed to you via your emails. Probably any ending notes from Alexander Barmak?
Yes. Good afternoon, everyone, again. At the end of the ExplAI 2025 workshop, I would like to take a moment to reflect on the past hours of the workshop. On behalf of the program committee, I want to express my sincere gratitude all of you for making this event such a success. We have had the privilege of listening to insightful keynote speeches and fascinating presentation on the latest advancements in explainable AI. The engaging discussion and questions have been truly inspiring, highlighting the vibrant and collaborative spirit of our community. A special thank you goes to all the authors who shared the valuable research, to our keynote speakers for the thought-provoking talks, and to every attendee for your active participation. I also want to extend our deepest appreciation to the General Chair, the entire organizing committee, program committee members, and the reviewers for their hard work and dedication in putting together this excellent program. We hope you leave this workshop with new ideas, new connections, and renewed motivation to continue your important work in this field. The future of explainable AI is bright, and it's thanks to the contribution of research like you. Thank you once again for being a part of ExplAI-2025. Thank you.
Thank you, Professor Barmak, for your kind words. Very sincere. Thank you very much. Perhaps a few closing remarks from our co-chair, Professor Krak.
I note that workshop was a great level in organization. Especially thank moderator Pavlo Raduk for very professional quality, and I have Mark young scientist in this workshop. It's our future, and there are very good result. I wish young scientists success, and I hope that result our first workshop will be good, will be better in the next time. Thank you very much.
I sincerely appreciate your lovely words. Thank you very much, Professor Krak. Dear participants, any other closing remarks, maybe questions? Okay, if none, then in summary, a few words from me. As we've today seen, the path to responsible human-centered innovation is a collaborative one. So I hope today has helped forge new connections and inspire new ideas. At this note, let's continue to work together to ensure that AI advances. It does so ethically, transparently, and in service of a sustainable future for all. Thank you once again. This officially concludes the ExplAI-2025 workshop. I wish you all safe travels, safe beings during the brutal invasion that Ukraine suffers. I hope you are being well right now, and wish you fruitful results in your future research. Thank you again, and have a nice day.
Thanks. Have a nice day.
Thank you.
Stop recorder, please.